On July 1st, 2025, a faint signal from the cosmos reached Earth, unnoticed by most. But to a vigilant few, it was the first whisper of a cosmic visitor. In the highlands of Chile, at an altitude where the air grows thin and the stars burn with crystalline clarity, the Atlas telescope stood sentinel against the darkness. Its mission, as mundane as it was vital, was to scan the heavens for asteroids that might threaten our world. Night after night, its robotic eye swept across the celestial sphere, cataloguing the eternal dance of distant lights. But on this particular evening, something extraordinary appeared in its field of view. The telescope's automated systems flagged an anomaly, a point of light moving against the fixed backdrop of stars with unusual speed and trajectory. Within hours, astronomers at the Minor Planet Center received the alert. What they saw in the preliminary data made them pause. The object's velocity was remarkable, far exceeding anything that should exist within the gravitational embrace of our Sun. Its path through space described not an ellipse, the signature of objects born within our solar system, but a hyperbola, a curve that spoke of origins beyond our celestial neighbourhood. If you're just as fascinated as we are by the incredible journey of 3i Atlas, hit that like button and subscribe so you never miss an update on the mysteries of space. Drop a comment below and let us know where you're listening from. Let's keep the cosmic conversation going. The Atlas system, an acronym for Asteroid Terrestrial Impact Last Alert System, represents humanity's early warning network against cosmic threats. Funded by NASA and operated through a network of 4 robotic telescopes scattered across the globe, these instruments conduct an endless vigil. Each night they photograph the entire visible sky, their computer algorithms comparing each new image against the last, searching for anything that moves. Most discoveries are routine, near-Earth asteroids, distant comets born in the outer reaches of our solar system, or satellites reflecting sunlight. But this object, initially designated as a candidate for closer study, would prove to be anything but routine. The telescope in Rio Hurtado, Chile, had captured the first clear images, but the international astronomical community quickly mobilized. Within days, observatories on every continent had turned their instruments toward this mysterious visitor. The Zwicky Transient Facility in California retrieved archived images from their databases, discovering they had photographed the object as early as May 21st, though no one had recognized its significance at the time. These pre-discovery observations proved invaluable, allowing astronomers to refine their calculations of its trajectory and confirm what the initial data had suggested. This object had travelled across the interstellar void to reach our solar system. As more observations poured in, a clearer picture emerged. The object moved with breathtaking speed, approximately 137,000 miles per hour relative to Earth, though this number would change dramatically as it fell toward the Sun. Its orbital eccentricity, a measure of how elongated its path through space appeared, registered at an astonishing 6.137. To put this in perspective, planets orbit the Sun with eccentricities close to zero, describing nearly perfect circles. Comets from the distant Oort cloud, the loosely bound reservoir of icy bodies at the edge of our solar system, might have eccentricities approaching 1. But values greater than 1 indicate a hyperbolic trajectory, an open curve that will never close. This object would pass through our solar system only once in its multi-billion-year existence, never to return. The discovery sparked immediate excitement within the astronomical community. Since the dawn of telescopic astronomy, humanity had observed only objects native to our solar system. Then, in 2017, a telescope in Hawaii detected Oumuamua, the first confirmed interstellar visitor. Its peculiar cigar shape and unexpected acceleration as it departed the inner solar system generated intense scientific debate and captured public imagination. 2 years later, amateur astronomer Gennady Borisov discovered 2I Borisov, the second interstellar object, which behaved more like a conventional comet. Now, this third visitor arrived, and astronomers raced to gather every possible observation before it vanished back into the cosmic depths. On July 2, 2025, the Minor Planet Center officially announced the discovery and assigned it the designation 3I Atlas. The I stood for interstellar, marking it as only the third confirmed object from beyond our solar neighborhood. The Atlas designation honored the survey that first detected it. But even as the announcement went public, uncertainty remained about the object's nature. Was it an asteroid? A dead chunk of rock and metal? Or was it a comet rich in volatile ices that would sublimate and glow as it approached the sun's warmth? Early observations provided conflicting signals. Some astronomers reported seeing no cometary features in their images, just a point of light moving against the stars. But on that same day, multiple observatories equipped with more sensitive instruments detected something remarkable. The Deep Random Survey in Chile, the Lowell Discovery Telescope in Arizona, and the massive Canada-France-Hawaii telescope atop Mauna Kea all reported the same finding. A faint diffuse cloud surrounding the object's nucleus, with hints of elongation suggesting a nascent tail. The object was active. It was a comet. Renowned comet hunters David Jewett and Jane Liu, using the Nordic Optical Telescope, confirmed the assessment. The object was clearly active, they reported, with a diffuse appearance inconsistent with a bare asteroid. As word spread, more telescopes joined the observation campaign. The Hubble Space Telescope, humanity's most famous observatory, turned its sharp eye toward the visitor. The James Webb Space Telescope, the most powerful infrared observatory ever built, scheduled observation time. Even spacecraft throughout the solar system prepared to glimpse this cosmic wanderer as it made its brief passage through our celestial realm. The confirmation that 3 Atlas was indeed a comet added layers of significance to its discovery. Comets are not simply pretty objects with glowing tails. They are time capsules, preserving in their frozen nuclei the pristine material from which planetary systems form. Every comet that astronomers study offers clues about the conditions that existed billions of years ago when worlds were being born. But a comet from another star system potentially carried secrets about alien suns, about the diversity of planetary formation, about whether the processes that created our home are common or rare in the cosmos. As July progressed and more data accumulated, the scientific community began to grasp just how extraordinary their discovery truly was. This was not merely another comet, not even merely another interstellar visitor. This object carried anomalies that would challenge conventional understanding and spark debates that continue to this day. The journey of 3I Atlas, from its origin in the depths of space to its momentary passage through our solar system, was about to reveal mysteries that would captivate scientists and the public alike, raising questions about the nature of cometary behaviour and, for some, even more profound questions about what truly travels between the stars. A comet, in its most essential form, is a frozen archive of ancient chemistry. When our solar system was young, some 4.5 billion years ago, the space between the newly forming sun and its orbiting planets teemed with gas and dust. As this primordial cloud began to cool and condense, ice formed in the outer regions where temperatures dropped below the freezing points of water, carbon dioxide, methane, and ammonia. These ices, mixed with rock and dust, aggregated into planetesimals, the building blocks from which planets eventually grew. But not all of this material found its way into planets. Some remained as wandering archives, pristine samples of our solar system's infancy, locked in deep freeze in the outer darkness. 3 Atlas, however, tells a different story. The chemistry frozen within its nucleus speaks of another stellar nursery, another disk of gas and dust swirling around a different sun in a different time. By examining the gases and dust it releases as sunlight warms its surface, astronomers can peer into the conditions that existed when that distant planetary system formed, potentially billions of years before our own sun ignited. As July turned to August in 2025, observations of 3I Atlas intensified. The Hubble Space Telescope captured a striking image on July 21st that would become iconic. The photograph showed a teardrop-shaped cocoon of dust and gas, surrounding the comet's nucleus, glowing softly against the black of space. The background stars appeared as streaks because Hubble had tracked the comet's motion, keeping it centered while the distant stellar backdrop moved through the frame. This technique, though it sacrificed the star's point-like appearance, revealed extraordinary detail in the comet's coma, the envelope of material surrounding its icy core. The coma's appearance provided crucial information. As a comet approaches the sun, solar radiation heats its surface, causing the most volatile ices to sublimate, transforming directly from solid to gas without passing through a liquid phase. This outgassing creates the coma, which can extend for tens of thousands of kilometers in every direction. Within the coma, sunlight scatters off tiny dust particles that were trapped in the ice and released during sublimation, creating the characteristic glow that makes comets visible even from great distances. Astronomers examining Hubble's images noted the reddish colour of 3I Atlas's coma, similar to what had been observed in 2E Borisov, the previous interstellar comet. This reddish hue suggested the presence of dust particles with specific compositional properties. Further analysis revealed that the coma was growing and changing as the comet continued its approach toward the Sun. On June 21st, when the comet was still relatively distant, observations by the Vera C. Rubin Observatory estimated the coma's diameter at approximately 13,000 kilometers. By early July, it had expanded to nearly 19,000 kilometers. Later observations from NASA's SphereX mission would reveal an even more dramatic expansion, with the coma reaching dimensions of nearly 26,400 by 24,700 kilometers, approaching twice Earth's diameter. But size was only part of the story. The James Webb Space Telescope, with its unprecedented infrared sensitivity, examined the comet's chemical composition in exquisite detail. Using its near-infrared spectrograph, Webb analysed the light passing through the comet's coma, breaking it into its component wavelengths like a prism separating sunlight into a rainbow. Each chemical species in the coma absorbs or emits light at characteristic wavelengths, creating a unique spectral fingerprint. Webb's observations revealed something remarkable. 3I Atlas was extraordinarily rich in carbon dioxide. The ratio of carbon dioxide to water ice in 3I Atlas measured approximately 8:1, among the highest ever recorded for any comet. This extreme ratio suggested something profound about where and when this comet formed. In the cold outer regions of a protoplanetary disk, far from the warmth of a nascent star, temperatures can drop low enough for carbon dioxide to freeze solid. Water ice, which forms at higher temperatures, would be less abundant in such regions. The composition of 3I Atlas therefore suggested it had formed in the outermost reaches of its home system, perhaps in a region analogous to our own Kuiper belt or even more distant. But there was more. Additional spectroscopic observations revealed the presence of neutral nickel in 3I Atlas's coma, and in surprisingly high abundances. Nickel had been detected in cometary atmospheres before, but never in such quantities. Even more puzzling, the expected companion, iron, appeared only in trace amounts. This high nickel-to-iron ratio was unusual, different from anything seen in solar system comets, or even in 2I Borisov. The presence of hydrogen cyanide was also confirmed, a molecule common in comets but important for understanding the comet's chemical evolution. Determining the physical size of 3I Atlas proved challenging. Direct imaging of a cometary nucleus, the solid icy core beneath the coma, requires resolving an object perhaps a few kilometers across, from distances of hundreds of millions of kilometers. Even Hubble, with its exceptional resolution, could not directly measure the nucleus. Instead, astronomers used indirect methods, analysing how much sunlight the nucleus reflected and making assumptions about its reflectivity. These calculations suggested a nucleus diameter somewhere between 440 meters and 5.6 kilometers, a wide range reflecting the uncertainties involved. What was certain, however, was the comet's velocity. Moving at 221,000 kilometers per hour when discovered, its speed would increase dramatically as the Sun's gravity accelerated it during its approach. At perihelion, its closest point to the Sun, 3I Atlas would reach velocities approaching 245,000 kilometers per hour. Yet even this tremendous speed would not be enough to escape the Sun's gravitational influence entirely. Or rather, it would escape, but just barely. The comet's hyperbolic excess velocity, the speed it would retain even at infinite distance from the Sun, measured approximately 58 kilometers per second. This value, significantly higher than those of the previous interstellar visitors, suggested that 3I Atlas was moving rapidly through the galaxy when it encountered our solar system, not leisurely drifting but racing through the interstellar medium. The comet's trajectory through our solar system would bring it to perihelion on October 29, 2025, at a distance of 1.4 astronomical units from the Sun just inside the orbit of Mars. Along the way, it would pass relatively close to Mars itself on October 3rd, approaching within roughly 29 million kilometers, close enough that spacecraft orbiting the red planet might capture images. After perihelion, its path would carry it past Venus and then Jupiter, before it escaped the solar system entirely, returning to the interstellar void from which it came. It posed no threat to Earth. The closest it would ever come to our planet would be approximately 269 million kilometers, safely beyond even Mars's orbit. As astronomers compiled these observations and measurements, a portrait of 3I Atlas emerged, a relatively large interstellar comet, rich in volatile carbon dioxide moving at high speed through our solar system on a trajectory that would allow only this single passage before it returned to the dark between the stars. Yet even as this basic understanding solidified, new observations were revealing features that would challenge conventional wisdom about how comets behave, setting the stage for debates that would captivate both the scientific community and the public imagination. To understand the significance of 3I Atlas, one must first understand the vastness of the journey it had undertaken. The space between stars is not truly empty, but it is profoundly lonely. The average distance between stars in our galactic neighbourhood spans several light-years, regions of space so immense that light itself, travelling at nearly 300,000 kilometres per second, requires years to cross them. Objects drifting through this interstellar medium encounter conditions fundamentally different from anything experienced within a planetary system. Near absolute darkness, temperatures hovering just a few degrees above absolute zero, and the constant bombardment of cosmic rays, high-energy particles accelerated to enormous velocities by violent cosmic events. When astronomers traced 3I Atlas's trajectory backward through space and time, they could identify the approximate direction from which it arrived. The comet emerged from the direction of the constellation Sagittarius, near the densely packed stars of the Milky Way's galactic centre. More specifically, orbital calculations suggested it originated from a region associated with the galaxy's thick disk, an older stellar population characterized by stars formed billions of years ago when our galaxy was young. This implied that 3I Atlas itself might be extraordinarily ancient, potentially older than our entire solar system. Determining an object's precise birthplace across galactic distances and timescales presents formidable challenges. Stars move through the galaxy on their own orbits around the galactic centre, their positions changing significantly over millions of years. Small uncertainties in measuring 3I Atlas's current trajectory compound rapidly when traced backward through time, and the gravitational influences of every star it might have passed near during its journey add layers of complexity. Nevertheless, the general picture remains clear. This comet formed around a different star, was somehow ejected from that system, and spent eons drifting through interstellar space before chance brought it into our solar neighbourhood. The process by which comets and other planetesimals are ejected from planetary systems is well understood in principle. During the chaotic early stages of planet formation, gravitational interactions between embryonic planets and smaller bodies can fling some objects into the outer reaches of a system or eject them entirely into interstellar space. Our own solar system almost certainly contributed trillions of comets to the interstellar population through such processes. Jupiter, massive and gravitationally powerful, likely played a particularly important role in this cosmic game of pinball, its influence scattering countless icy bodies outward during our system's youth. If every star system produces a similar population of interstellar wanderers, then space between the stars should teem with them, a vast reservoir of ancient ice and rock adrift in the cosmic darkness. Recent estimates suggest that trillions upon trillions of such objects might inhabit our galaxy alone, though they remain effectively invisible unless one happens to pass through a star system where telescopes can detect it. The discovery of 3 interstellar objects in just 8 years suggests that our improving detection capabilities are beginning to glimpse this hidden population. 3I Atlas's velocity relative to the local standard of rest, the average motion of stars in our galactic neighbourhood, measured at approximately 58 kilometers per second. This value exceeds those of both previous interstellar visitors. Oumuamua moved at 26 kilometers per second, while 2I Borisov travelled at 32 kilometers per second. The higher velocity implies that 3 Atlas had been moving through the galaxy for a very long time, accumulating kinetic energy, or perhaps being accelerated by gravitational encounters with massive objects in its past. One of the most intriguing aspects of 3I Atlas's trajectory was its orientation relative to our solar system. The plane of its orbit, when it entered our system, lay within approximately 5 degrees of the ecliptic, the plane defined by Earth's orbit around the Sun and shared roughly by all the planets. For a randomly arriving interstellar object, any orientation should be equally likely, making the probability of such close alignment relatively small, perhaps around 1 in 50. This coincidence prompted discussion among astronomers. Was it truly just chance, or might some subtle dynamical effect favour such alignments? Adding to the peculiarity, 3 Atlas's trajectory brought it relatively close to several planets during its passage. It would pass Mars at a distance of roughly 29 million kilometres, then swing past Venus at about 97 million kilometres, and finally approach Jupiter at 54 million kilometres before departing the system. While none of these encounters were particularly close by planetary standards, the sequence of near passes to multiple planets struck some observers as statistically unusual for a randomly arriving object. The comet's retrograde orbit added another layer of interest. Unlike the planets and most solar system objects, which orbit the Sun in the same direction that the Sun rotates, 3 Atlas moved in the opposite direction. This retrograde motion is not unprecedented. Comets from the Oort cloud often display random orbital orientations, including retrograde paths, but for an interstellar visitor moving nearly parallel to the ecliptic plane yet in reverse, the configuration seemed distinctive. As 3 Atlas continued its inward journey through the summer of 2025, astronomers calculated that it had been travelling through space for billions of years. If it originated in the galaxy's thick disk as its trajectory suggested, it might have formed 7 billion years ago or more, making it substantially older than our 4.5 billion-year-old solar system. For billions of years, it had drifted alone through the darkness, its surface bombarded by cosmic rays, its ices slowly modified by the harsh interstellar radiation environment. The material frozen within it had remained largely unaltered since the epoch when its parent planetary system was young, a time capsule from an era when our own Sun and planets had not yet formed. The journey across interstellar space had not been without consequence. Cosmic rays, high-energy protons and atomic nuclei accelerated to nearly the speed of light by supernova explosions and other violent events, constantly pelted the comet's surface. Over millions of years, this radiation could alter the surface chemistry, breaking molecular bonds and creating new compounds. The cold, hard vacuum of space would have slowly stripped away the most volatile surface materials through sublimation, driven by the faint warmth of starlight and the impact of interstellar particles. By the time 3I Atlas entered our solar system, its surface had been processed and modified by its long isolation, though the deeper interior presumably still preserved more pristine material from its formation. Now, after eons of darkness, the comet had returned to light. As it fell toward our Sun, solar radiation began to warm its ancient surface, driving sublimation and releasing gases and dust that had been frozen for billions of years. These exhalations from 3I Atlas's nucleus would provide astronomers with their only opportunity to sample material from another star system, to analyze chemistry from a planetary system that formed under potentially very different conditions from our own. The molecules and dust particles streaming from the comet carried information about temperatures, pressures, and chemical processes from a different cosmic environment, offering a window into the diversity of planetary formation across our galaxy. As autumn approached and 3 Atlas drew ever closer to the Sun, excitement built within the astronomical community. The comet would pass perihelion in late October, reaching its point of maximum activity. But even as standard observations confirmed its broadly cometary nature, new images were beginning to reveal a feature that would challenge assumptions and spark intense scientific debate. A jet of material clearly visible in high-resolution images, pointing not away from the Sun as cometary tales always do, but directly toward it. The anomaly first appeared in the Hubble Space Telescope images from July 21st, though its significance was not immediately apparent. When David Jewett and his colleagues examined the high-resolution photographs, they noticed something unusual about the comet's coma. Rather than showing the expected symmetric glow around the nucleus, with a tail extending in the antisolar direction, the images revealed an elongated structure, approximately 10 times longer than it was wide, oriented at a small angle toward the Sun. This geometry suggested not a diffuse coma, but a directed jet of material being expelled from the comet's nucleus in the Sun's direction. In August, the 2-meter twin telescope at Teide Observatory in the Canary Islands captured even clearer evidence. Combining 159 separate exposures of 50 seconds each, the resulting image showed the comet's dark nucleus surrounded by a bright coma, and within that coma, a fan-shaped structure extending toward the Sun. The jet appeared to stretch approximately 6,000 kilometers from the nucleus, a substantial feature clearly distinguishable from the expected antisolar tail. Observatory director Michael Serra-Ricard confirmed the detection and began analysing its properties. This observation marked a pivotal moment. Comets, in their classical form, behave predictably. As they approach the Sun, solar radiation heats their surfaces, causing volatile ices to sublimate. The resulting gases and entrained dust particles initially expand outward in all directions, forming the coma. But then solar radiation pressure and the solar wind, the stream of charged particles flowing outward from the Sun, push the gas and dust away from the Sun, creating the characteristic cometary tail that always points in the anti-solar direction. This behaviour has been observed and understood for centuries. A jet pointing toward the Sun contradicts this basic physics. Yet there it was, clearly visible in multiple independent observations, a stream of material flowing from 3I Atlas's nucleus toward the Sun, defying the expected behaviour. The discovery immediately raised questions. What physical process could produce such a feature? Was this truly unprecedented, or had similar structures been observed before but perhaps not recognised? And most importantly, what did it reveal about the nature of 3I Atlas itself? Some astronomers quickly offered explanations within the framework of conventional cometary physics. One possibility involved the concept of a synchrone, a curve in space traced out by dust particles, all released from the comet's nucleus at the same time. Depending on the particles' sizes and velocities, and on the observer's viewing angle, such structures could sometimes create the illusion of material extending sunward. If Earth's position relative to the comet happened to align just right, the broad fan of a dust tail could appear foreshortened, with some material seeming to point toward the Sun. Another possibility concerned the size distribution of particles being ejected. Solar radiation pressure affects small dust particles much more strongly than large ones. Micron-sized dust grains would be pushed rapidly away from the Sun, contributing to the conventional tail. But larger particles, perhaps 100 microns or more in diameter, would respond much more sluggishly to radiation pressure. If the comet were ejecting predominantly large particles, perhaps through explosive outbursts of subsurface gas, these particles might spread along the comet's orbital path in both directions, creating a band of material that included a sunward component. The rotation of the comet's nucleus added another factor to consider. Comets spin on their axes, and if active regions or vents on the nucleus happen to be oriented favourably, they could eject material preferentially in certain directions. As the nucleus rotated, these jets would sweep through space like water from a rotating lawn sprinkler, potentially creating complex patterns in the coma. If one of these rotating jets happened to be aimed roughly sunward at the time of observation, it might produce the observed feature. Nevertheless, several aspects of the sunward jet troubled some researchers. The structure appeared quite collimated, meaning it was relatively narrow and directed rather than diffuse. This suggested a concentrated outflow from a specific source region on the nucleus. Moreover, the feature persisted across multiple observations separated by weeks, implying either sustained activity from a fixed source region or very slow-moving particles that remained visible for extended periods. Both scenarios required somewhat special conditions. Harvard astrophysicist Avi Loeb took particular interest in the anomaly. In a series of blog posts and public statements, he highlighted what he termed the anti-tail as potentially significant. Loeb noted that if the sunward jet consisted of conventional cometary dust reflecting sunlight, solar radiation pressure should push these particles rapidly away from the Sun, making a persistent sunward structure difficult to explain. He and colleague Eric Quito published a technical analysis exploring various scenarios, including the possibility that the jet might contain unusually large or dense particles, less susceptible to solar radiation pressure, or even that some unconventional physical process might be at work. Loeb's commentary sparked broader public interest in 3I Atlas, particularly given his previous high-profile statements about Oumuamua, the first interstellar visitor, which he had suggested might potentially be artificial in origin. While careful to present multiple possibilities, Loeb framed the sunward jet as an anomaly worthy of serious scientific attention, something that might not fit neatly within standard cometary behaviour. He assigned 3I Atlas a rating on what he termed the Loeb scale, a subjective measure of how anomalous an interstellar object appeared, placing it at 4 out of 10. The broader astronomical community responded with more measured assessments. Michael Serra-Ricard, whose telescope had captured some of the clearest images of the jet, stated plainly that the feature was normal for comets. Jets are pointing to the sunward direction, and the comet's tail in the anti-solar direction, he explained, emphasizing that both features could coexist without requiring any exotic physics. The fan-shaped appearance in his images, he noted, resulted from the comet's rotation spreading the jet's ejecta across a range of angles. Other comet researchers echoed this interpretation. The presence of jets on cometary nuclei is well established. Missions to solar system comets have directly imaged active regions ejecting material into space. The European Space Agency's Rosetta mission, which orbited comet 67P Churyumov-Gerasimenko for 2 years, observed numerous jets emanating from the comet's surface, some persisting for months while others appeared and disappeared over short timescales. These jets result from localized sublimation of ices, often concentrated in specific regions where surface composition or topography favors enhanced activity. What made 3I Atlas's case noteworthy was not necessarily the presence of a sunward jet per se, but rather the prominence and persistence of this feature in observations. Whether this reflected something unusual about 3I Atlas's composition, structure, or activity level, or whether it simply represented a particularly photogenic example of a phenomenon that occurs in many comets, but often goes unnoticed, remained a matter of interpretation and ongoing analysis. As August gave way to September, the scientific community intensified its scrutiny of 3I Atlas, and the debate over its unusual features began to crystallize into distinct perspectives. On one side stood the majority of comet specialists, confident that the observed phenomena fell comfortably within the envelope of known cometary behaviour, perhaps unusual but not unprecedented. On the other stood a smaller but vocal group, led by figures like Avi Loeb, who argued that the constellation of anomalies associated with 3I Atlas merited serious consideration of alternatives to purely natural explanations. The mainstream interpretation emphasized that comets are inherently variable and complex objects. No two comets behave identically, and the sample size of well-studied comets remains relatively small. 3I Atlas might be rich in carbon dioxide, but so are several solar system comets, particularly those originating from the outer reaches of the planetary system. Its sunward jet might be prominent, but jets pointing in various directions relative to the Sun have been observed on other comets. Its trajectory might align somewhat with the ecliptic plane, but this could easily be coincidental given the small number of interstellar objects discovered to date. Moreover, the scientific method demands that extraordinary claims require extraordinary evidence. Suggesting that an interstellar object might be something other than a natural body represents an extraordinary claim, one that should only be seriously entertained when all conventional explanations have been thoroughly tested and found wanting. In the case of 3I Atlas, the conventional explanation remained robust. This was simply an interstellar comet, likely formed billions of years ago in another planetary system, ejected into interstellar space, and now passing through our solar system on its way back to the cosmic void. The argument for taking the anomalies seriously rested on a different philosophical foundation. Science progresses, this camp argued, not by assuming everything fits existing frameworks, but by paying careful attention to outliers and anomalies. History is replete with examples of phenomena initially dismissed as mundane that later revealed profound new physics. The strange properties of Mercury's orbit eventually led to general relativity. The anomalous rotation curves of galaxies pointed toward dark matter. Careful attention to details that don't quite fit has often proven the path to discovery. Loeb and colleagues compiled what they termed a comprehensive list of 3I Atlas's unusual properties. Beyond the sunward jet, they noted the extreme carbon dioxide to water ratio, higher than any previously measured comet, the unusual nickel to iron ratio in its gas emissions, the nearly ecliptic alignment of its trajectory despite retrograde motion, the sequence of relatively close planetary passes, and the absence of measurable non-gravitational acceleration despite vigorous outgassing. Each anomaly individually might have a conventional explanation, but collectively they argued the pattern deserved deeper investigation. The debate extended into the realm of comparative analysis. When 2I Borisov, the previous interstellar comet, passed through our solar system in 2019, astronomers had found it remarkably ordinary. Its behaviour, composition and properties all matched those of solar system comets so closely that it provided strong evidence for the universality of cometary physics. Planetary formation processes, it seemed, produced similar objects regardless of which star system hosted them. But 3I Atlas appeared more distinctive. Its high carbon dioxide ratio, its unusual metal emission lines, its prominent sunward jet, these features set it apart not only from solar system comets, but also from 2I Borisov. Part of the challenge in resolving the debate stemmed from the limitations of available data. Despite the numerous observations collected since its discovery, 3 Atlas remained a distant, faint object barely visible even to the largest telescopes. Determining its exact size required assumptions about its reflectivity. Characterizing its composition depended on analyzing faint spectral features in the glow of its coma. Understanding the dynamics of its sunward jet required detailed modelling based on sparse observations. More data would certainly help, but time was running short. The comet would reach perihelion in late October, pass behind the Sun from Earth's perspective, and then begin its outward journey, growing fainter with each passing week. The scientific process handling the 3I Atlas debate proceeded through its established channels. Researchers submitted papers to peer-reviewed journals presenting analyses and interpretations. Conference presentations allowed for detailed technical discussions. Preprint servers made preliminary findings available for community scrutiny, even before formal publication. This system, refined over centuries, provides the mechanism through which scientific consensus gradually forms, with evidence and argument winnowing away less supported hypotheses while reinforcing those that withstand critical examination. What made the 3I Atlas case particularly engaging for the public was its accessibility as a story. Here was an object from another star system, visible in our own cosmic neighbourhood, displaying behaviour that prompted genuine scientific debate about its nature. Unlike many controversies in modern astrophysics that involve abstract concepts like dark energy or quantum fluctuations in the early universe, this debate centred on something tangible, a wandering ice ball from an alien planetary system, doing something unexpected. The questions it raised touched on fundamental issues. How common are planetary systems? How similar are they to ours? What can we learn about cosmic diversity from studying visitors from other stars? These questions resonated beyond the specialist community. As October arrived and 3I Atlas continued its approach toward the Sun, both sides of the debate prepared for what they hoped would be decisive observations. The comet's passage near Mars on October 3rd would provide spacecraft orbiting the red planet with opportunities for closer looks. The perihelion passage on October 29th would represent the peak of the comet's activity, potentially revealing features invisible at greater distances. ESA's JUICE spacecraft en route to Jupiter was positioned to observe the comet in November after perihelion, when it might display the effects of its close solar encounter. Each of these observation opportunities carried the potential to provide new insights that might either confirm the conventional interpretation or deepen the mysteries surrounding this enigmatic visitor from the stars. The October 3rd flyby of Mars marked a turning point in humanity's observation of 3I Atlas. The European Space Agency's ExoMars Trace Gas Orbiter, designed to study the Martian atmosphere from an altitude of just a few hundred kilometres, turned its colour and stereo surface imaging system toward a target 30 million kilometres distant. The spacecraft's cameras, optimised for photographing rock formations and dust storms on the Martian surface, struggled with the faint distant comet. Yet even through the limitations of instruments pressed far beyond their intended use, the images revealed something that would transform scientific understanding of what they were witnessing. The CASIS instrument captured a series of exposures showing 3I Atlas as a slightly fuzzy white dot against a field of streaked stars. But it was not the comet's brightness that captured attention. It was the geometry of its appearance. Even in these difficult images taken from an unprecedented vantage point with Mars between Earth and the approaching comet, the elongated structure that had puzzled astronomers for months remained clearly visible. More importantly, the Martian perspective confirmed what many had suspected, but few had wanted to acknowledge. The feature was not an optical illusion dependent on Earth's viewing angle. The sunward jet was real, structural, and persistent. Back on Earth, larger telescopes with more sophisticated instruments continued their vigil. The twin 10-meter mirrors of the Keck Observatory in Hawaii, among the most powerful optical telescopes on the planet, captured images with unprecedented clarity. These photographs revealed the full extent of what astronomers were now calling the anti-tail, a term borrowed from rare but documented cases in solar system comets where specific viewing geometries could create the appearance of material extending sunward. But the anti-tail of 3I Atlas dwarfed these historical precedents in both size and persistence. The structure extended not merely thousands of kilometers but tens of thousands of kilometers from the comet's nucleus, a narrow collimated stream of material clearly distinguishable from the more diffuse coma surrounding the nucleus. Computer analysis of the images revealed that the anti-tail maintained a nearly constant orientation toward the Sun across observations separated by weeks, suggesting either an extraordinarily stable jet or particles moving so slowly that they remained visible long after their ejection. Understanding this phenomenon required detailed physical modelling. When ice sublimate from a cometary nucleus, the expanding gas carries dust particles with it. The initial velocity of this material depends on the temperature and composition of the sublimating ice, with carbon dioxide sublimation typically producing faster outflows than water ice. Once ejected, the particles and gas molecules enter the realm of forces that will determine their ultimate fate. The comet's weak gravity, attempting to pull them back, the momentum imparted by the sublimating gas, pushing them away, and solar radiation pressure, the subtle but persistent push of sunlight. For small particles, micron-sized grains of dust and ice, solar radiation pressure dominates. Photons from the Sun carry momentum, and when they strike and are absorbed or reflected by a particle, they transfer that momentum, creating a force that pushes the particle away from the Sun. This force acts continuously, and for small particles with large surface area relative to their mass, quickly accelerates them to high velocities in the anti-solar direction. These particles form the bright, sweeping tails that make comets spectacular in the night sky, tails that can extend for millions of kilometers and always point away from the Sun regardless of the comet's direction of motion. But larger particles tell a different story. A dust grain 100 microns across, 10 times larger than those that form typical cometary tails, has 1,000 times more mass relative to its surface area. Solar radiation pressure still pushes it, but much more weakly. Such particles drift slowly away from the nucleus, spreading along the comet's orbital path. Some move ahead of the nucleus, others fall behind. From certain viewing angles, these particles create what astronomers call a neckline structure, or synchronic band, material distributed along the orbit that can appear to extend in various directions, depending on the observer's position. Could this explain 3I Atlas's anti-tail? The mathematics suggested it might, under specific conditions, if the comet were ejecting predominantly large particles, and if those particles were being expelled preferentially in certain directions by rotating jets on the nucleus, and if Earth's viewing geometry happened to align fortuitously, then perhaps the appearance of a sunward jet could be reconciled with known physics. But each if represented an assumption, a special condition required to make the conventional explanation work. Alternative models produced different conclusions. If the anti-tail consisted not of dust but primarily of gas, or perhaps of extremely small particles effectively coupled to the gas flow, then solar radiation pressure would affect it differently. Gas molecules and very small particles could be accelerated to high velocities by the expanding carbon dioxide sublimating from the nucleus. If concentrated into a narrow jet by the geometry of the sublimation source, this material could extend sunward for considerable distances before radiation pressure and the solar wind finally dispersed it. The bright green colour that began appearing in some observations of the comet during this period suggested that gas might indeed play a significant role. Yet this explanation too required special circumstances. Cometary jets typically expand rapidly, becoming diffuse within a few thousand kilometers of the nucleus. Maintaining a collimated structure across tens of thousands of kilometers implied either an unusually powerful and concentrated source or some mechanism for confining the flow. Neither seemed particularly likely, though neither could be definitively ruled out with available data. The debate over the anti-tail's nature extended beyond academic journals and conference presentations. Avi Loeb continued to draw public attention to what he characterized as an unresolved anomaly. In a series of widely circulated essays, he posed direct questions to the astronomical community. If the anti-tail could be explained by conventional physics, why had comparable structures not been prominently observed in the many comets studied over centuries of astronomy? Why did the feature appear so stable and persistent, rather than variable and short-lived as jets typically are? Why were there no detailed quantitative models demonstrating that known processes could produce exactly what was being observed? These questions highlighted a fundamental tension in how science approaches anomalies. The burden of proof in science typically falls on those proposing new explanations, not on those defending established frameworks. Conventional cometary physics had explained countless observations over decades of study. That it might struggle to account for one unusual feature in one object did not necessarily invalidate the framework. Unusual does not mean impossible. Rare does not mean unnatural. The universe contains multitudes, and any sufficiently large sample will include outliers. But Loeb's questions also reflected a legitimate concern about complacency. Science can sometimes dismiss anomalies too readily, explaining them away with just-so stories, rather than subjecting them to rigorous analysis. The history of astronomy includes embarrassing episodes where unusual observations were ignored or misinterpreted because they didn't fit prevailing theories, only to later reveal fundamental new phenomena. The strange spectra of quasars were initially dismissed as instrumental artifacts. The acceleration of the universe's expansion seemed so unlikely that it was double-checked exhaustively before acceptance. Caution is warranted, but so is attention to details that don't quite fit. As October progressed and 3I Atlas drew ever closer to the Sun, the anti-tail remained one of several features that distinguished this interstellar visitor from its predecessors. The phenomenon had catalyzed important discussions about cometary physics, about how thoroughly we understood these ancient ice balls, and about whether our models captured the full range of possible behaviors. Whether the anti-tail represented a profound mystery or simply an unusual but natural configuration of a particularly active comet remained unresolved. But there was no doubt it had captured imaginations, both within the scientific community and among the broader public watching this cosmic visitor make its singular passage through our celestial neighbourhood. The sunward jet glowed in images beamed down from telescopes around the world and in orbit above Earth's obscuring atmosphere, a luminous finger pointing toward our star, defying the wind and radiation that should have swept it away. Whatever its ultimate explanation, it stood as a reminder that the universe still held surprises, that objects formed around distant suns billions of years ago could arrive in our cosmic backyard and challenge our understanding, and that the scientific process of observation, analysis, debate, and synthesis remained humanity's best tool for unraveling the mysteries, written in light across the darkness of space. While the anti-tail captured headlines and sparked debates about cometary dynamics, a quieter revolution was unfolding in the spectroscopic analysis of 3I Atlas's composition. Every molecule absorbs and emits light at characteristic wavelengths determined by its quantum mechanical properties. By dispersing the light from the comet's coma into its component colours and measuring the precise pattern of bright and dark lines, astronomers could identify which chemical species were present and in what relative abundances. What they found in 3I Atlas challenged expectations and raised profound questions about the chemistry of planet formation in other stellar systems. The James Webb Space Telescope's observations in early August had revealed the comet's extraordinary carbon dioxide abundance, but Webb's instruments focused primarily on infrared wavelengths, where molecules like carbon dioxide, water, and carbon monoxide leave strong signatures. Complementary observations at visible and ultraviolet wavelengths told a different chemical story, one that grew stranger as more data accumulated. In mid-August, spectrographs at major observatories detected strong emission lines from neutral nickel atoms in 3I Atlas's coma. Nickel emission had been observed before in comets, discovered only recently in 2021 when astronomers analysing archival spectra from comets dating back decades realised they had been missing this signal all along. The mechanism producing the nickel emission involves photodissociation of nickel-containing molecules by solar ultraviolet radiation. But the strength of the nickel emission from 3I Atlas exceeded anything previously measured. The comet was releasing nickel at prodigious rates. More puzzling still was the absence of corresponding iron emission. In typical solar system materials, iron and nickel occur together in characteristic ratios, legacy of their nucleosynthetic origins in stellar interiors. They form together in the fusion reactions of massive stars and are expelled together in supernova explosions that scatter heavy elements through space. In solar system comets, when nickel emission is detected, iron emission accompanies it, usually at higher levels since iron is more abundant than nickel in cosmic material. But Thrusi Atlas showed strong nickel lines and barely detectable iron. The disparity suggested something unusual about either the comet's composition or the chemistry occurring in its coma. One possibility involved metal carbonyl compounds, exotic molecules where metal atoms bind to carbon monoxide groups. Nickel forms a particularly stable compound called nickel tetracarbonyl, composed of one nickel atom surrounded by 4 carbon monoxide molecules. This compound, discovered in terrestrial industry in the 19th century, is volatile enough to exist as a gas at relatively low temperatures and could potentially survive in cometary ices. If 3I Atlas contained significant quantities of nickel tetracarbonyl while lacking the corresponding iron carbonyl compounds, which are somewhat less stable, this might explain the observed emission pattern. As the comet warmed and these exotic molecules sublimated, ultraviolet sunlight would break apart the nickel tetracarbonyl, releasing neutral nickel atoms that would then fluoresce, producing the observed emission lines. The lower abundance of iron carbonyl would mean less iron available for similar emission. But this explanation raised as many questions as it answered. How would substantial amounts of nickel tetracarbonyl form in a cometary environment? In industrial processes on Earth, nickel tetracarbonyl is synthesized by exposing metallic nickel to carbon monoxide at specific temperatures and pressures. The conditions in a forming planetary system differ vastly from industrial reactors, yet somehow 3I Atlas appeared to contain these unusual compounds. If it had formed in the cold outer reaches of its home protoplanetary disk, as its high carbon dioxide ratio suggested, perhaps the abundant carbon monoxide in such regions had reacted with metallic nickel grains under those specific conditions. But this remained speculative, untested against detailed chemical models. Additional observations revealed other unusual spectral features. Emission from cyanogen, a molecule composed of 2 carbon atoms bonded to 2 nitrogen atoms, appeared stronger in 3I Atlas than in typical comets. Hydrogen cyanide emission was also detected, though this molecule occurs commonly in comets and thus seemed less anomalous. The ratio of different carbon-bearing species, carbon dioxide, carbon monoxide, cyanogen, hydrogen cyanide, differed from the patterns observed in solar system comets, suggesting either different formation conditions or different evolutionary processing during the billions of years the comet spent in interstellar space. The organic chemistry of comets has long fascinated scientists because of its implications for the origin of life. Comets contain complex carbon compounds, including amino acids and other prebiotic molecules. Impacts of comets on the early Earth may have delivered crucial ingredients for life's emergence. Understanding the chemical diversity of comets from different stellar environments bears directly on questions about how common, life-friendly chemistry might be throughout the galaxy. But 3 Atlas's chemistry seemed to point in a direction different from simple organic richness. The dominance of carbon dioxide over water, the presence of unusual metal compounds, the specific pattern of emission lines, these suggested an environment during formation quite unlike the region where Earth and the other terrestrial planets accreted. If 3I Atlas represented typical material from the outer reaches of its home system, then that system's chemistry differed substantially from our own solar systems. This implied that planetary systems might be more diverse in their chemical makeup than previously assumed, with implications for the potential habitability of planets forming from such material. Laboratory simulations of cometary chemistry attempted to reproduce the observed emission patterns. Researchers created synthetic cometary ices, freezing together water, carbon dioxide, carbon monoxide, and various other compounds in ratios matching those inferred for 3 Atlas. They then subjected these mixtures to ultraviolet radiation and warming to simulate solar heating, measuring the resulting emission spectra. Some experiments successfully reproduced aspects of 3I Atlas's spectrum, demonstrating that conventional chemical processes could potentially explain the observations. But perfect matches remained elusive, suggesting that some details of the comet's composition or the chemistry occurring in its coma remained inadequately understood. The mystery deepened with observations of temporal variability in the emission patterns. The strength of various spectral features changed over hours and days, indicating that the comet's outgassing was not steady but fluctuated, perhaps as different regions on the rotating nucleus came into and out of sunlight, or as subsurface reservoirs of volatile ices became exposed and then depleted. This variability added complexity to the interpretation, since any complete model needed to account not just for what chemicals were present, but how their release varied with time. One particularly intriguing observation came from high-resolution spectroscopy that could distinguish between molecules moving toward and away from Earth through the Doppler shift of their emission lines. These observations revealed that different chemical species had different velocity distributions in the coma. Carbon dioxide appeared to be moving faster than water vapor, consistent with its lower molecular weight and the physics of gas expansion. But some metal emission appeared to come from relatively slow-moving material, suggesting it might be associated with larger dust particles or with gas that had been decelerated by collisions after initial ejection. These subtle velocity differences provided clues about the physical structure of the coma and the processes driving the outgassing. As the various chemical observations accumulated through late summer and into autumn, they painted a picture of 3I Atlas as chemically distinct not only from most solar system comets, but also from 2I Borisov, the previous interstellar visitor. While Borisov had appeared remarkably similar to solar system comets in its composition and behavior, 3I Atlas stood apart. Whether this reflected fundamental differences between their respective home systems, or perhaps different evolutionary paths, perhaps 3I Atlas had spent longer in the harsh interstellar environment, or had formed under more extreme conditions, remained uncertain. The chemical signatures encoded in the light from 3I Atlas constituted messages from another world, literally. The molecules fluorescing in its coma had been assembled billions of years ago in a protoplanetary disk orbiting a star perhaps hundreds of light-years distant. They had been frozen into a comet during that system's planet-forming epoch, then preserved in the deep freeze of interstellar space for eons before solar warming released them. Every emission line carried information about conditions in that distant nursery, about temperatures and pressures, about the abundance of heavy elements in that region of the galaxy, about the specific sequence of chemical reactions that built complex molecules from simpler precursors. Decoding those messages required painstaking work, combining observations with theoretical chemistry and laboratory experiments. The task was far from complete, but even the preliminary results revealed tantalizing hints of diversity in the chemical cosmos, of planetary systems built from different recipes, and of the complex interplay between stellar nucleosynthesis, interstellar chemistry, and planet formation that generates the rich tapestry of chemical compositions found throughout the universe. In late August, amateur astronomers around the world began reporting a striking change in 3I Atlas's appearance. The comet, which had glowed with a predominantly reddish hue in July and early August, was transforming. Images captured with backyard telescopes and sensitive cameras showed the coma taking on a distinct green colour, a transformation that became more pronounced as September arrived and the comet continued its approach toward the Sun. This colour shift, while beautiful, was not merely aesthetic. It represented fundamental changes in the chemistry and physics occurring within the comet's atmosphere, changes driven by its increasing exposure to solar radiation as it plunged deeper into the inner solar system. The red colour that characterized 3I Atlas during the early weeks after its discovery arose from the scattering of sunlight by dust particles in its coma. These particles, microscopic fragments of rock and organic material released as ice sublimated from the nucleus, scattered red light more efficiently than blue light, similar to how Earth's atmosphere scatters sunlight to produce red sunsets. The specific shade of red provided information about the size distribution and composition of the dust particles. Detailed analysis of the early observations had shown that 3I Atlas's dust resembled that of 2I Borisov and various solar system comets, with particle sizes centered around 100 microns and a composition consistent with silicate minerals mixed with organic compounds. But as the comet approached within 2 astronomical units of the Sun, roughly twice Earth's distance from our star, a new phenomenon began to dominate its appearance. Green emission started emerging from the inner coma, the region closest to the nucleus where gas density remained high, and solar ultraviolet radiation was beginning to drive energetic chemical reactions. This green glow arose from a specific molecule, diatomic carbon, two carbon atoms bonded together, designated C2 by chemists. Diatomic carbon exists rarely on Earth. It is reactive and short-lived under terrestrial conditions, but in the vacuum of space and under intense ultraviolet bombardment, it flourishes. The molecule forms in cometary comae through a cascade of reactions, beginning with larger organic molecules present in the nucleus. As ice sublimate and carry these organics into the coma, solar ultraviolet photons break apart the larger molecules, fragmenting them into smaller species. Some of these fragments recombine to form diatomic carbon. The C2 molecule has a strong electronic transition that causes it to absorb ultraviolet light and re-emit that energy as green, visible light, creating the characteristic cometary green glow observed in many active comets. The appearance of green emission in 3I Atlas thus signaled that its activity level was increasing, that sublimation rates were climbing as solar heating intensified, and that the photochemistry in its coma was transitioning from the relatively quiescent state that characterized its more distant observations to the energetic state typical of comets near perihelion. Time-lapse images captured over days and weeks showed the green color intensifying and the green region expanding, growing from a small spot near the nucleus to a broad envelope encompassing the entire inner coma. But the green glow revealed more than just increasing activity. Careful spectroscopic observations showed that the C2 emission had a specific spatial distribution within the coma, concentrated in certain regions and weaker in others. This non-uniform distribution indicated that the production of C2 was not uniform across the nucleus surface, but instead occurred preferentially in areas where particular types of organic material were concentrated. The rotating nucleus brought these active regions into and out of sunlight, causing the C2 emission to vary in strength with the rotation period. Another green-emitting species also appeared in spectra during this period, the hydroxyl radical, designated OH, which consists of one oxygen atom bonded to one hydrogen atom. Hydroxyl forms in cometary comae through the photodissociation of water molecules. Solar ultraviolet photons strike water molecules in the coma and break them apart, producing hydroxyl and atomic hydrogen. Like C2, hydroxyl has electronic transitions that produce green emission, and the two species together dominate the green color of active comets. The ratio of C2 to OH emission provides information about the comet's composition, specifically about the ratio of organic carbon to water ice in its nucleus. Comets with high C2OH ratios are considered carbon-rich, while those with low ratios are carbon-depleted. Initial measurements of 3I Atlas showed relatively high C2OH ratios, consistent with its known carbon dioxide, richness and suggesting that organic carbon compounds were abundant in its nucleus. This carbon-rich nature reinforced the picture of a comet formed in the cold outer regions of its home protoplanetary disk, where carbon compounds could condense and be incorporated efficiently into growing comet nuclei. The transformation from red to green created spectacular visual displays in images captured by both professional observatories and amateur astronomers. The comet's bright green inner coma contrasted with its reddish outer coma and the faint anti-solar tail, creating a striking multicolored appearance. These images circulated widely on social media and science news outlets, bringing 3I Atlas to the attention of audiences far beyond the astronomical community. The interstellar visitor was no longer just an object of scientific interest, but a visual phenomenon, a reminder that the universe offers beauty as well as mystery. Yet beneath the aesthetic appeal lay deeper questions. The intensity of 3I Atlas's green emission exceeded that of many solar system comets at similar distances from the Sun, suggesting unusually high production rates of C2 and OH. If these production rates accurately reflected the abundance of parent molecules in the nucleus, then 3I Atlas might be extraordinarily rich in both water and organic compounds, despite its carbon dioxide dominance. Alternatively, the intense green glow might indicate unusually efficient photochemical processing, perhaps due to the specific geometric configuration of the comet's jets or unusual dust properties that affected the ultraviolet radiation field within the coma. Time series observations revealed another fascinating aspect of the color transformation. It was not monotonic. The comet did not simply transition from red to green and stay green. Instead, the relative contributions of red and green emission varied over hours and days, creating a dynamic, evolving color palette. During some observation periods, the green emission would surge, dominating the comet's appearance and making it appear as a brilliant emerald jewel against the black of space. At other times, the green would fade somewhat, allowing the red dust scattering to become more apparent. These variations correlated with changes in the comet's overall brightness, suggesting they reflected real fluctuations in outgassing rates rather than merely observational artifacts. The physical cause of these fluctuations likely involved the interaction between solar heating and the comet's rotation. As the nucleus spun, different regions would be exposed to sunlight at different times. Areas with high concentrations of volatile ices would outgas strongly when illuminated, producing surges in green emission. Less volatile regions or areas covered by dust mantles would produce less gas, leading to dimmer periods. The rotation period of 3I Atlas remained poorly constrained. Measuring rotation from brightness variations is challenging when a comet is highly active, as the changing gas and dust production can overwhelm the signal from the rotating nucleus, but hints in the photometric data suggested a period somewhere between 6 and 12 hours. By late September, as 3 Atlas closed to within 1.5 astronomical units of the Sun, the green emission reached peak intensity. The comet had become one of the brightest objects in its region of sky, visible through modest amateur telescopes as a distinctly green, fuzzy star with a faint tail extending away from the Sun. Professional observations continued to pour in from observatories worldwide, each adding pieces to the puzzle of this interstellar visitor's composition and behavior. The green glow, born of ancient organic molecules forged in a distant stellar system billions of years ago, now fluoresced under the light of our Sun, a transient bridge between worlds separated by unimaginable gulfs of space and time. The mounting accumulation of unusual features in 3I Atlas, the persistent anti-tail, the anomalous chemical composition, the intense green emission, the nearly ecliptic trajectory, inevitably sparked speculation that extended beyond conventional astronomical frameworks. In online forums, social media discussions, and even some fringe publications, questions emerged. Could this object be something other than a natural comet? Might it represent technology from another civilization, either deliberately sent to our solar system, or perhaps a derelict craft drifting through space like the Flying Dutchman of cosmic legend? Such speculation was not entirely without precedent in the scientific community. When Oumuamua, the first confirmed interstellar object, displayed unexpected non-gravitational acceleration as it departed the inner solar system in 2018, Avi Loeb and colleague Shmuel Bialy published a paper in the Astrophysical Journal Letters exploring whether the observed acceleration could be explained if Oumuamua were not a natural body but rather a light sail, a thin sheet of material pushed by solar radiation pressure. The paper carefully noted that natural explanations remained possible, but it argued that the artificial hypothesis should not be dismissed without consideration. The paper sparked intense controversy, with most astronomers arguing that extraordinary claims required extraordinary evidence and that Oumuamua's behavior could be adequately explained by natural processes. Now, with 3I Atlas displaying its own set of anomalies, similar discussions emerged. Loeb himself had been vocal about the object's unusual properties, compiling what he termed a comprehensive list of features deserving serious scientific attention. While carefully stating that natural explanations should be explored thoroughly, he also argued that the possibility of an artificial origin should not be excluded a priori. He described 3 Atlas as a potential Trojan horse, an object masquerading as a natural comet while potentially being something more. The specific hypothesis took various forms depending on who articulated it. In its most restrained version, the suggestion was simply that 3I Atlas might contain unusual materials or structures not typically found in natural comets, perhaps representing a chance encounter with some form of space debris from an advanced civilization. More elaborate versions proposed that the object might be an active probe, deliberately entering our solar system to gather information, with its cometary appearance serving as camouflage. The most speculative version suggested it might be a form of interstellar transport, a mothership carrying technology, or even biological material between star systems, using its icy exterior as both radiation shielding and propellant. These ideas were met with profound skepticism by the vast majority of the astronomical community. The principle of Occam's razor, that the simplest explanation consistent with the evidence should be preferred, argued strongly against invoking extraterrestrial technology when natural explanations remained viable. Every anomaly associated with 3i Atlas, however unusual, fell within the range of behaviour that could plausibly arise from natural cometary physics and chemistry. The anti-tail could result from large dust particles or specific viewing geometries. The unusual chemical composition could reflect formation conditions in a different stellar environment. The green emission was standard cometary photochemistry. The trajectory alignment with the ecliptic, while statistically unlikely, was not impossible. After all, given enough interstellar objects, some will inevitably arrive with unusual orientations simply by chance. Moreover, the artificial hypothesis faced severe challenges from the observational evidence. If 3i Atlas were a spacecraft or contained technology, one might expect to observe signals inconsistent with natural processes, radio emissions, directed propulsion, course corrections, or physical structures incompatible with a natural body. None of these had been detected despite careful searches. The object's behaviour matched that of an actively outgassing comet in essentially all respects. Its trajectory, while unusual, followed pure gravitational dynamics, with no evidence of the non-gravitational accelerations that might indicate active manoeuvring. Spectroscopic observations showed emissions consistent with ice and rock, not industrial materials or exotic propellants. The scientific method provides a framework for evaluating extraordinary claims through what can be termed the ladder of hypotheses. At the bottom rung cite explanations invoking only well-established physics and observed phenomena, in this case, natural cometary processes. Higher rungs involve increasingly speculative mechanisms, poorly understood natural processes, exotic natural phenomena not yet directly observed, and ultimately explanations requiring intelligence or technology. Scientists properly focus attention on lower rungs until evidence compels climbing higher. For 3i Atlas, despite its anomalies, natural explanations remained firmly viable, leaving no compelling reason to ascend to more exotic hypotheses. Yet the discussion served valuable purposes beyond its immediate subject. It highlighted the challenge of detecting genuinely artificial objects if they ever do enter our solar system. It prompted consideration of what observable signatures would definitively distinguish technology from natural phenomena. It forced examination of implicit assumptions about how thorough our understanding of cometary physics truly is. And it engaged public interest in a way that purely technical astronomical discussions rarely achieve. The question, could it be aliens, draws attention even when the answer is almost certainly no. The debate also revealed broader concerns about how science communicates uncertainty to the public. When scientists say that something is unlikely or implausible, they mean something specific. Given current evidence and established theory, this explanation has low probability. But in public discourse, these terms can be heard as we don't really know, or even we're covering something up, particularly when prominent scientists make statements that seem to take unconventional possibilities seriously. Managing this communication challenge is crucial for maintaining public trust, while honestly acknowledging the limits of scientific knowledge. Several astronomers published detailed technical papers analysing specific aspects of 3i Atlas's behaviour and demonstrating that natural processes could account for observations. One study showed that the anti-tail could be reproduced in models if the comet ejected dust particles with a specific size distribution dominated by grains around 100 microns. Another demonstrated that the nickel emission could be explained if the comet contained nickel-bearing minerals that sublimated at specific temperatures without requiring exotic compounds like nickel tetracarbonyl. A third calculated that the ecliptic alignment, while unlikely for any individual object, was not so improbable given the expected population of interstellar objects passing through the solar system over millions of years. These papers did not definitively prove that 3i Atlas was a natural comet. Science rarely deals in absolute proof, but they showed that the natural explanation remained robust and internally consistent. The artificial hypothesis, by contrast, required positing entities and technologies for which no independent evidence existed, explaining the observations by invoking unknowns rather than knowns. From a Bayesian perspective, where hypotheses are evaluated based on both how well they fit the data and their prior probability, the natural explanation maintained overwhelming support. As October advanced and 3 Atlas approached perihelion, the window for additional observations before the comet passed, behind the Sun, was closing. Both sides of the debate looked toward these final pre-perihelion observations with anticipation. Would they reveal new anomalies that deepened the mystery, or would they provide the missing pieces that allowed natural explanations to fully account for all observed features? The comet itself remained indifferent to human speculation, following its predetermined trajectory according to the implacable laws of gravity and thermodynamics, its ices sublimating, its coma glowing, its anti-tail pointing sunward, regardless of whether observers below believed it to be a chunk of ice from a distant planetary system or something altogether more extraordinary. By mid-October 2025, as 3 Atlas plunged toward its October 29th perihelion, the object had become one of the most intensively studied astronomical targets in history. More telescope time had been devoted to this single comet than to any previous transient astronomical event, save perhaps the 1987 supernova in the Large Magellanic Cloud. Yet for all the observations, all the spectra and images and photometric measurements, fundamental questions remained unresolved. The cosmic visitor that had arrived unannounced in early summer had revealed itself to be more enigmatic than anyone anticipated, a puzzle wrapped in ice and dust hurtling through the inner solar system on its way back to the interstellar void. The challenge in studying interstellar objects stems from their transient nature. Unlike planets or stars or galaxies, which remain available for observation indefinitely, interstellar visitors spend mere months in the inner solar system, where they are bright enough for detailed study. 3I Atlas would be accessible for perhaps 6 months total, the 3 months before perihelion when it approached and brightened, and 3 months afterward as it receded. Beyond that window, it would fade below the detection threshold of even the largest telescopes, becoming just another invisible chunk of ice lost in the cosmic dark. Every observation had to be conducted during this brief interval, and any question left unanswered would remain unanswered forever. This urgency drove the unprecedented observational campaign. Ground-based telescopes on every continent allocated time to observe the comet. Space telescopes including Hubble, Webb, Spherex and TESS all made 3I Atlas a priority target. Spacecraft throughout the solar system, from Mars orbiters to the distant JUICE mission en route to Jupiter, planned observations. Even amateur astronomers contributed, their backyard telescopes and cameras capturing images that, while less detailed than professional observations, provided valuable additional data points and enabled monitoring on timescales and frequencies impossible for oversubscribed professional facilities. Yet despite this flood of data, interpretation remained challenging. Each observation answered some questions while raising others. The anti-tail's persistence confirmed it was real and structural, not an optical illusion, but the precise mechanism producing it remained debated. The chemical composition measurements revealed the comet's unusual abundances, but whether these reflected different formation conditions, different stellar metallicity, or evolutionary processing during its interstellar journey remained uncertain. The intense green emission demonstrated high activity levels, but converting measured emission rates into physical production rates required detailed modelling of the coma's density structure, temperature distribution, and radiation field, all quantities that could not be measured directly. One particularly vexing challenge involved determining the comet's rotation period and the orientation of its rotation axis. These parameters are crucial for understanding the observed variability and for modelling how solar heating drives the outgassing. But measuring rotation from light curves is difficult for highly active comets because variations in gas and dust production can overwhelm the signal from the rotating nucleus. Multiple groups attempted to extract rotation information from the photometric data, but they arrived at inconsistent results, with estimates ranging from 6 hours to more than 20 hours. Without better constraints on rotation, detailed models of the comet's activity remained underdetermined. The size of the nucleus presented similar challenges. Hubble observations had provided an upper limit of approximately 5.6 kilometers diameter and a lower limit of 440 meters. But this wide range reflected fundamental uncertainties about the nucleus's reflectivity. A bright, highly reflective nucleus would need to be smaller to produce the observed brightness, while a dark, poorly reflective nucleus would need to be larger. Without direct resolved images of the nucleus separate from the bright coma surrounding it, constraining the size more precisely was impossible with current observations. These uncertainties cascaded through all derived quantities. The mass of the nucleus, crucial for understanding its gravitational influence on ejected material and for calculating its trajectory evolution over millions of years, depended on both size and assumed density. The total volatile inventory, how much ice the comet contained, and how much it would ultimately release before becoming inert, required knowing the nucleus size and composition. The timescale for evolution, how long the comet could remain active, depended on these same uncertain parameters. The fundamental mystery, however, transcended these technical challenges. It concerned not just what 3I Atlas was, but what it represented. Was this object typical of interstellar comets, a representative sample of the trillion upon trillion icy bodies thought to drift through the galaxy? Or was it an outlier, an unusually unusual specimen that revealed little about the broader population? With only 3 confirmed interstellar objects discovered to date, Oumuamua, Tusah, Borisov, and now 3 Atlas, each dramatically different from the others, drawing conclusions about the typical properties of such objects remained impossible. Oumuamua had been small, dark and elongated, with no detected coma or outgassing despite passing well within Earth's orbit. Its categorization as either an asteroid or a heavily processed comet remained disputed. Tusah Borisov had been large, bright and thoroughly comet-like, resembling solar system comets so closely that it seemed to confirm the universality of cometary physics. 3 Atlas fell somewhere between, clearly a comet with vigorous outgassing, but with properties and behaviours that set it apart from the template established by Borisov and most solar system comets. Statistical predictions suggested that powerful new survey telescopes coming online in the next few years, particularly the Vera Rubin Observatory, with its large mirror and wide field of view, might detect several interstellar objects per year. If these predictions proved accurate, within a decade astronomers might have observed dozens of such visitors, enough to begin characterizing the population statistically. Only then would it become clear whether 3I Atlas represented a common type, a rare variant, or something in between. But that future knowledge remained years away. For now, astronomers worked with what they had: a wealth of observations of a single object whose properties challenged easy interpretation. The scientific papers emerging from the 3I Atlas campaign reflected this ambiguity, filled with careful hedging. May indicate, consistent with, could result from, might reflect. The language of uncertainty pervaded the technical literature because certainty remained elusive. As October 29th approached and 3 Atlas prepared to round the Sun, at its closest approach, all eyes turned toward what that perihelion passage might reveal. Would the increased solar heating and intense radiation environment near perihelion trigger new phenomena, perhaps fragmentation of the nucleus, dramatic increases in outgassing, or changes in the antitail structure? Would the observations from spacecraft and telescopes positioned to view the comet near perihelion finally provide the missing pieces that would allow a complete, consistent model of its behaviour? Or would 3I Atlas, even at perihelion, maintain its enigmatic character, revealing enough to tantalize but not enough to fully satisfy? The comet approached its appointment with the Sun indifferent to human curiosity, following the trajectory determined billions of years ago when gravitational interactions in some distant planetary system flung it into interstellar space. What it would show us in these final days before passing behind the Sun and emerging into the post-perihelion sky remained to be seen. The puzzle was not yet solved, the cosmic mystery not yet fully illuminated, though the perihelion passage offered one last best opportunity to probe the secrets held within this ancient ice from another world. The final days of October 2025 arrived with an electric tension in the astronomical community. 3I Atlas, having travelled across light years of interstellar void and then plunged through the outer solar system over the preceding months, now approached the moment that would define its singular passage through our cosmic neighbourhood. On October 29th, at approximately 1437 Universal Time, the comet would reach perihelion, its closest approach to the Sun, passing at a distance of 1.4 astronomical units, roughly 210 million kilometres, just inside the orbit of Mars. For a comet, this moment represents both culmination and transformation, the point of maximum solar heating and therefore maximum activity, when the battle between ice and radiation reaches its peak intensity. The trajectory that brought 3I Atlas to this appointment had been calculated and recalculated hundreds of times since the comet's discovery in early July. Astronomers had refined the orbit using thousands of position measurements from observatories worldwide, achieving precision that would have seemed impossible just decades earlier. They could predict the comet's position at perihelion to within a few kilometers, an extraordinary accuracy for an object that had traveled trillions of kilometers to reach this point. The orbit itself told a story of gravitational choreography, the elegant mathematics of celestial mechanics playing out across the solar system. In the weeks leading up to perihelion, 3i Atlas had been racing sunward along a trajectory that carried it high above the ecliptic plane from the perspective of its incoming direction, then curved downward to pass through that plane near perihelion before climbing back above it during departure. This path meant that different telescopes had optimal viewing geometries at different times. In September, Northern Hemisphere observatories had excellent views as the comet moved through constellations visible in their evening skies. By mid-October, as the comet's angular separation from the Sun decreased and it moved lower toward the horizon, Southern Hemisphere facilities gained advantage. Now, as perihelion approached, the comet was becoming increasingly difficult to observe from Earth, its position in the sky placing it too close to the Sun's overwhelming glare. The geometry presented both challenges and opportunities. On one hand, the comet's proximity to the Sun in Earth's sky meant that ground-based observations would soon become impossible, leaving a crucial gap in coverage during the perihelion period itself. The Sun's brightness would completely overwhelm the comet's light for any telescope attempting to observe from Earth's surface or even from Earth orbit. This blackout period would last approximately 2 weeks, from late October through mid-November, during which 3i Atlas would pass behind the Sun from our perspective, experiencing its moment of maximum solar exposure hidden from direct observation. But this same geometry created opportunities for spacecraft. Several missions were positioned to observe the comet from vantage points where the Sun would not interfere. ESA's Mars Express and ExoMars Trace Gas Orbiter had already captured images during the October 3rd flyby of Mars. Now, as the comet continued inward, other spacecraft prepared to observe. The Parker Solar Probe, NASA's mission to study the Sun's corona from unprecedented proximity, found itself in an orbital position that might allow observations if the comet passed through its field of view. The SOHO spacecraft, stationed at the L1 Lagrange point between Earth and Sun, had coronagraphic instruments designed to block sunlight while imaging the solar corona, and these might potentially detect 3i Atlas if its trajectory carried it into the field of view. The physical changes occurring within 3i Atlas as it approached perihelion were dramatic and accelerating. The comet had been active since at least May, when the earliest pre-discovery observations showed hints of a coma. But activity had intensified exponentially as solar distance decreased. Each step closer to the Sun brought a disproportionate increase in solar energy flux. At 3 astronomical units, the comet received 1/9 the solar energy per unit area that Earth receives. At 2 AU, that increased to 1/4. At 1.5 AU, more than 4/10. Now approaching 1.4 AU at perihelion, the comet experienced nearly half the solar intensity that warms Earth's surface. This increasing energy drove the sublimation of progressively less volatile ices. Early in the comet's approach, only the most volatile species, carbon dioxide, carbon monoxide, sublimated readily. As solar heating intensified, water ice began contributing significantly to the outgassing. At perihelion, even more refractory materials might begin to sublime, species that had remained frozen throughout most of the comet's journey. The total gas production rate, measured by the brightness and extent of the coma, had been climbing steadily, with estimates suggesting the comet was releasing hundreds of kilograms of material per second by late October. The nucleus itself was experiencing thermal stress. Cometary nuclei are not solid, uniform blocks of ice but rather loosely consolidated aggregates, often described as rubble piles, held together more by mutual gravitational attraction than by structural strength. As solar heating penetrated the surface layers, the ice sublimated and escaped, but the process was not uniform. Some regions, perhaps with higher concentrations of dark, heat-absorbing material, warmed faster than others. This differential heating created thermal stresses, and the pressure of sublimating gas beneath the surface could fracture the already weak material. Cometary fragmentation, where the nucleus breaks apart under these stresses, is not uncommon. Several famous comets have fragmented during perihelion passage, some breaking into multiple large pieces that continued as separate comets, others disintegrating entirely into clouds of dust and vapour. The possibility that 3I Atlas might fragment added urgency to the pre-perihelion observations. If the nucleus did break apart, its behaviour would change dramatically, and the opportunity to observe an intact interstellar cometary nucleus would be lost. Every observation before perihelion thus carried additional weight. It might be the last view of 3 Atlas in its original form. The scientific teams operating the various telescopes and spacecraft coordinated their observation plans to maximise coverage while minimising duplication. Hubble would capture high-resolution images in the days immediately before the sun's glare made observation impossible. The Gemini South Telescope in Chile, with its exceptional image quality and sensitive instruments, would push observations to the last possible moment, tracking the comet deep into twilight. Webb's infrared capabilities would probe the comet's thermal emission, measuring how efficiently it radiated away the absorbed solar energy. Ground-based radio telescopes would search for emissions from water, carbon monoxide, and other molecules, providing complementary data on composition and production rates. Amateur astronomers around the world also participated in this final observation campaign. While their equipment lacked the sophistication and sensitivity of professional facilities, they could provide continuous monitoring impossible for oversubscribed major telescopes. Networks of amateur observers tracked the comet's brightness, colour and coma structure throughout each night, creating a detailed record of short-term variability. Their images, while less detailed than professional photographs, captured the comet's overall appearance and documented changes occurring over hours and days. As October 28th gave way to October 29th, and the countdown to perihelion entered its final hours, 3I Atlas was in a sky position that made observation increasingly difficult from most locations. The comet had brightened to approximately 8th magnitude, theoretically visible through binoculars, but practically impossible to see, given its proximity to the Sun. The last good ground-based observations came from telescopes in Chile, where clear skies and excellent atmospheric conditions allowed imaging through the twilight. These final images showed a comet in full, vigorous activity, its green coma extending tens of thousands of kilometers from the nucleus, its anti-tail still visible pointing sunward, its conventional dust tail streaming millions of kilometers in the anti-solar direction. Then, as Earth rotated and the sun rose over Chile, 3I Atlas disappeared into the solar glare. For the next 2 weeks the comet would be invisible from Earth, hidden by our star's overwhelming brightness. It would pass through perihelion unwatched by human eyes, experiencing its moment of maximum transformation in privacy. When it emerged on the other side in mid-November, returning to the morning sky before sunrise, what would observers see? Would the comet have survived perihelion intact, or would it have fragmented? Would it be brighter, having survived intact and now outgassing furiously, or dimmer, perhaps depleted of its most volatile ices? The answers lay days in the future, beyond perihelion, when 3 Atlas would once again swim into view and reveal what the sun's fire had wrought. Though 3I Atlas had disappeared from Earth-based telescopes' view, the scientific observations did not cease. In the void beyond our planet, instruments continued their vigil, gathering data that would prove crucial for understanding the comet's behaviour during its most extreme environment. The Hubble Space Telescope, orbiting Earth above the obscuring atmosphere, had captured what would be the last high-resolution images before perihelion on October 26th. These photographs revealed extraordinary detail in the comet's structure, showing not just the bright central coma, but subtle features in the jets and fans of material streaming from the nucleus. The Hubble images displayed the comet's dual nature with striking clarity. The green inner coma, produced by C2 and OH emission from freshly sublimated material close to the nucleus, glowed brilliantly in the centre of the field. Surrounding this green heart, the reddish outer coma extended outward, its colour arising from sunlight scattered by larger dust particles that had been pushed away from the nucleus by gas pressure and were now drifting more slowly under the influence of solar radiation. The contrast between these regions revealed the spatial structure of the coma's chemistry, showing where different physical processes dominated. But it was the tail structures that commanded particular attention. The conventional anti-solar dust tail, now extending more than 1 million kilometers behind the comet, showed clear striations, parallel streamers indicating episodes of enhanced dust ejection in the comet's past. These striations formed because dust particles released at the same time follow similar trajectories, creating coherent streams that remain distinguishable for weeks or months. By measuring the position of each striation relative to the nucleus and knowing the particles' speeds, astronomers could reconstruct the timing of past outbursts, essentially reading the comet's recent activity history, encoded in the geometry of its tail. The antitail, the sunward jet that had caused such fascination and debate, remained prominent in these final Hubble images. New processing techniques applied to the data revealed that the feature had a complex fine structure with multiple narrow streams rather than a single broad jet. This structure suggested that several active regions on the nucleus were contributing to the sunward emission, each producing its own collimated outflow. The discovery of this fine structure lent support to natural explanations for the anti-tail, as it resembled the multiple jet structures observed by spacecraft at solar system comets. The Gemini South Observatory in Chile, perched atop Cerro Pachon at an altitude of 2,700 meters, pushed observations to the absolute limit of what was physically possible from Earth's surface. On the evening of October 28th, with the comet now less than 10 degrees from the Sun in the sky, the Gemini telescope tracked 3I Atlas through the twilight. The observation required exceptional skill from the operators. Pointing too close to the Sun risked damaging the sensitive instruments, while waiting too long meant the comet would be lost in the glare. The resulting images captured 3I Atlas at a critical moment, hours before perihelion, when solar heating had reached nearly maximum intensity. These last light images showed changes from just days earlier. The coma appeared asymmetric, brighter on the sunward side, suggesting that the nucleus might be beginning to preferentially shed material from its most intensely heated face. The green emission had intensified further, indicating accelerating production of C2 and OH as sublimation rates climbed. Careful photometry showed that the comet had brightened by nearly half a magnitude in the previous 24 hours, an acceleration in activity that suggested the comet was approaching a critical threshold where the heating penetrated deep enough to access fresh, volatile-rich material beneath any surface crust. The Very Large Telescope, ESO's flagship facility in Chile's Atacama Desert, contributed spectroscopic observations that provided the most detailed chemical information yet obtained. Using its powerful UV spectrograph, VLT captured high-resolution spectra showing dozens of emission lines from various molecular species. The ratios of these lines allowed astronomers to estimate the temperature and density of gas in different regions of the coma. The measurements revealed that gas temperatures near the nucleus exceeded 200 Kelvin, well above the sublimation temperature of water ice, confirming that sublimation was proceeding vigorously. Further from the nucleus, the gas cooled through expansion, dropping to temperatures around 50 Kelvin at distances of several thousand kilometers. One particularly intriguing finding from the VLT spectra concerned the isotopic composition of the comet's water. Isotopes are variants of chemical elements with different numbers of neutrons in their nuclei. For hydrogen, the most common isotope has 1 proton and no neutrons, while deuterium has 1 proton and 1 neutron. The ratio of deuterium to ordinary hydrogen in water, the DH ratio, carries information about where and under what conditions the water formed. Early solar system regions close to the Sun had low DH ratios, while more distant, colder regions had higher ratios. By measuring 3I Atlas's DH ratio, astronomers could infer something about conditions in its home protoplanetary disk. The VLT measurements suggested a DH ratio somewhat higher than Earth's ocean water, but not as high as some solar system comets, particularly those from the Oort cloud. This intermediate value was puzzling. It might indicate that 3I Atlas formed at intermediate distances in its home system, not in the extreme cold of the outer disk. Or it might reflect mixing of material from different regions during the planet formation process. Or perhaps the interstellar radiation environment had somehow altered the isotopic ratios during the comet's billions of years in space, though the mechanisms for such alteration remained poorly understood. As terrestrial telescopes completed their observations and the comet slipped into the Sun's glare, attention shifted to space-based assets positioned to maintain surveillance during the perihelion blackout. The SOHO spacecraft, a joint ESA-NASA mission that had been monitoring the Sun continuously since 1996, operated several coronagraphic cameras designed to block the Sun's bright disk, while imaging the much fainter corona. These instruments had serendipitously discovered thousands of small comets passing near the Sun over SOHO's decades of operation. Now, predictions suggested that 3I Atlas might pass through the outer edge of SOHO's field of view during perihelion. The predictions proved accurate. On October 29th, as 3I Atlas rounded the Sun at perihelion, SOHO's LASCO C3 coronagraph captured a series of images showing a faint, elongated object moving across the starfield. The comet appeared much fainter in SOHO's images than in conventional telescopes. The spacecraft's instruments were optimized for coronal emission rather than comet observation, but the detection was unambiguous. For a few precious hours, humanity maintained visual contact with the interstellar visitor during its closest solar approach, a reminder that even when circumstances conspire to hide celestial events from direct observation, ingenuity and appropriate technology could pierce the veil. The SOHO images revealed that 3I Atlas had survived the first phase of perihelion passage intact. There was no sign of catastrophic fragmentation, no sudden brightening or development of multiple distinct condensations that would indicate the nucleus had broken into separate pieces. The comet's coma remained coherent, and while the tail structure was difficult to discern in SOHO's relatively low-resolution images, the overall morphology appeared consistent with continued normal activity. The nucleus, it seemed, had withstood the thermal stress and remained as a single body, at least through perihelion itself. Yet survival through perihelion did not guarantee continued survival. The hours and days immediately following closest approach would be critical. Many comets that survive perihelion intact subsequently fragment due to delayed effects, the continued sublimation of gas from beneath a weakened surface, crust, or the expansion of internal fractures created by thermal stress. The true test of 3I Atlas's structural integrity would come in the post-perihelion period, after it emerged from behind the Sun and returned to visibility from Earth. Only then would observers be able to assess whether the nucleus remained intact or had broken into fragments during or shortly after its solar encounter. The perihelion passage of 3I Atlas represented more than just the comet's closest approach to the Sun. It marked a turning point in the object's behaviour and in humanity's ability to study it. Before perihelion, the comet had been approaching, brightening, becoming easier to observe each week. After perihelion, it would be receding, fading, becoming progressively more difficult to study. The window of opportunity for detailed observations was closing. Whatever secrets 3 Atlas still held would need to be extracted from observations made during its outward journey, before distance and dimness rendered it once again invisible, returning it to the darkness from which it had so briefly emerged. In the days immediately following perihelion, as 3 Atlas began its outward journey and slowly separated in angle from the Sun, astronomers monitored the first scattered reports from the few telescopes positioned to catch early glimpses of the comet's post-perihelion state. These initial observations carried enormous significance. They would reveal whether the comet had survived its closest solar approach intact, and they would show what changes, if any, the intense heating had wrought. The astronomical community watched with anticipation, knowing that what they were about to witness might either confirm their understanding of cometary physics or reveal yet another surprise from this most enigmatic of interstellar visitors. The first reliable observations came from spacecraft and from observatories positioned at high southern latitudes, where the geometry favoured early detection. ESA's JUICE mission, currently navigating its long journey toward Jupiter, had manoeuvred to optimize its viewing angle of 3I Atlas. Between November 2nd and November 7th, JUICE's cameras and spectrometers captured images and spectra of the comet, now beginning its outward trek from the inner solar system. The spacecraft's distance from both the comet and the Sun provided a unique perspective, allowing observations without the interference of Earth's atmosphere or the complication of trying to see the comet against bright twilight skies. The JUICE observations revealed a comet transformed. The images showed that 3I Atlas remained structurally intact. There was no evidence of fragmentation into multiple pieces, but its appearance had changed dramatically. The coma had expanded significantly, now extending more than 100,000 kilometers from the nucleus, nearly twice its pre-perihelion extent. The green emission from C2 and OH had reached peak intensity, indicating that water and carbon compound sublimation rates were at their highest levels yet observed. The dust production had also surged, with the antisolar tail now stretching more than 1.5 million kilometers, clearly visible in JUICE's wide-field images. But the most striking change concerned the anti-tail, the sunward jet that had dominated discussion throughout the comet's approach. In the JUICE images, this feature appeared diminished, less prominent than in pre-perihelion observations. The jet had not disappeared entirely, but it was noticeably fainter and shorter than before. Detailed analysis of the images suggested that the anti-tail now extended only about 30,000 kilometers from the nucleus, compared to the 60,000 kilometers or more observed in late October. The structure's relative brightness compared to the main coma had also decreased, making it harder to detect against the glowing background. As additional observations accumulated over the following days, this trend became unmistakable. The anti-tail was fading. By November 10th, when Thriss Atlas had moved far enough from the Sun in Earth's sky to become accessible to ground-based telescopes in the pre-dawn hours, observers reported difficulty detecting the sunward jet at all. Images from the Gemini North Telescope in Hawaii, carefully processed to enhance faint structures, showed at most a weak, diffuse glow extending sunward from the nucleus, nothing like the pronounced collimated jet visible a month earlier. The feature that had caused such intense scientific debate and public fascination was transitioning, transforming into something different. Simultaneously, the conventional anti-solar dust tail was becoming increasingly prominent. As the comet moved away from the Sun and the viewing geometry changed, the tail's full extent became apparent. Ground-based wide-field cameras captured images showing the tail stretching across several degrees of sky, a faint but discernible streak of reflected sunlight, marking the path of dust particles pushed away from the nucleus by solar radiation. The tail displayed beautiful structure, with multiple streamers indicating episodic outbursts of enhanced dust production, creating a record of the comet's recent activity history written across the sky. The transition from a prominent sunward jet to a more conventional cometary appearance sparked immediate scientific analysis. Several explanations presented themselves. One possibility involved the changing illumination geometry. As the comet passed perihelion and began moving away from the Sun, the angle at which sunlight struck the nucleus changed. Active regions that had been preferentially illuminated during approach might now be partially in shadow, reducing their contribution to the observed jets. If the sunward jet had originated from specific localized sources on the nucleus, changes in illumination could substantially affect its prominence. Another explanation concerned the evolution of the surface itself. The intense heating at perihelion might have altered the nucleus surface, creating or thickening an insulating crust of dust and refractory material left behind as volatile ices sublimated. Such a crust could suppress outgassing from some regions while allowing it to continue from others, potentially changing the distribution of active areas and thus the appearance of jets. The formation of thermal crusts is well documented in solar system comets and represents a natural evolution as surfaces are processed by solar heating. A third possibility involved the depletion of the most volatile materials near the surface. The carbon dioxide that dominated 3I Atlas's composition sublimate readily at temperatures well above those at which water ice becomes active. During the approach to perihelion, carbon dioxide-rich regions might have outgassed particularly vigorously, creating the observed sunward jet. By post-perihelion, these near-surface reservoirs of highly volatile material might have been depleted, reducing the vigor of outgassing from those regions and diminishing the jet's prominence. Deeper, water-rich material would continue sublimating, but with different spatial and velocity distributions, potentially explaining the more conventional post-perihelion appearance. Whichever explanation or combination of explanations proved correct, the observed transition carried important implications. It demonstrated that the anti-tail had not been a static feature, but rather a dynamic phenomenon, dependent on the specific conditions of the comet's state and environment. This variability argued against interpretations that had suggested the anti-tail indicated something fundamentally unusual about 3I Atlas's nature. Natural cometary processes, responding to changing illumination and evolving surface conditions, could apparently produce both the prominent sunward jet observed pre-perihelion and its subsequent diminishment. The scientific community responded to these observations with considerable interest. Those who had maintained that the anti-tail represented normal cometary behavior, explainable through conventional physics, pointed to the transition as vindication. The fading of the jet and the emergence of more typical cometary features suggested that 3I Atlas was, after all, following expected patterns, just with unusual prominence of features that might occur more subtly in other comets. The object had perhaps not been as anomalous as some had suggested, merely an example of the natural diversity within cometary phenomena. But others noted that many questions remained unanswered. Why had the sunward jet been so much more prominent in 3I Atlas than in other well-studied comets? What specific configuration of composition, structure, and activity had produced the observed features? Could the same processes occur in solar system comets under appropriate conditions, or did something about 3I Atlas's origin and history make it particularly prone to such behaviour? The comet's appearance had answered some questions while raising others, a common outcome in science where each new observation illuminates even as it reveals the extent of remaining ignorance. As November progressed and 3I Atlas continued its outward journey, the comet began the long fade that would eventually return it to invisibility. The peak brightness, achieved shortly after perihelion, gave way to steady dimming as solar distance increased. The coma slowly contracted as sublimation rates declined in response to decreasing solar heating. The dust tail persisted, gradually becoming thinner and fainter as the finite supply of dust ejected near perihelion spread out along the comet's orbit. By late November, 3I Atlas had faded to about 10th magnitude, still visible through modest telescopes but no longer the prominent object it had been at peak activity. The transformation of the comet's appearance, particularly the transition from a prominent anti-tail to a more conventional cometary morphology, became a central theme in the growing body of scientific literature emerging from the 3 Atlas observing campaign. Multiple research groups published detailed analyses attempting to model the observed changes using varying assumptions about nucleus composition, structure, and rotation. These papers demonstrated that plausible natural mechanisms could reproduce at least the broad features of the observations, though perfect quantitative agreement between models and data remained elusive, a common situation in cometary science, where the complexity of real objects often exceeds what simplified models can fully capture. Beyond the telescopes and scientific journals, 3I Atlas captured public imagination in ways that transcended its astronomical significance. The comet became a cultural phenomenon, discussed not merely in specialized forums but in mainstream media, on social networks, in casual conversations. For a few months in late 2025, an object from another star system commanded the attention of millions, reminding humanity of its place in a vast and ancient cosmos, and demonstrating the enduring power of celestial phenomena to inspire wonder and curiosity. News outlets worldwide covered the comet's perihelion passage as a major story. Major newspapers ran feature articles explaining what interstellar objects were and why 3I Atlas mattered. Television networks broadcast special reports, bringing in astronomers as expert commentators to explain the science behind the spectacular images. Online news sites published photo galleries showcasing the best images from professional observatories and accomplished amateur astronomers, allowing global audiences to witness the comet's beauty and complexity. The coverage varied in sophistication and accuracy. Some outlets provided excellent nuanced reporting that captured both the science and the sense of wonder, explaining the chemistry of cometary comae, the physics of tails and jets, and the significance of studying interstellar visitors. Other coverage leaned toward sensationalism, emphasizing the more speculative theories about the comet's nature, and sometimes conflating possibility with likelihood in ways that distorted the scientific discourse. Headlines screamed about alien motherships and mysterious visitors, often burying the more measured scientific assessments in favor of attention-grabbing speculation. Social media amplified both the interest and the confusion. Images of 3I Atlas, particularly those showing its brilliant green coma and prominent tails, circulated widely on platforms like Twitter, Instagram, and Facebook. Amateur astronomers shared their photographs, some of remarkable quality, demonstrating that modern amateur equipment could capture impressive detail when wielded by skilled hands. These images often garnered tens of thousands of shares and likes, introducing the comet to audiences far beyond those who would normally follow astronomical news. But social media also became a vector for misinformation and wild speculation. Unfounded claims about the comet's nature proliferated, ranging from the merely inaccurate to the frankly bizarre. Some posts claimed the comet would pass dangerously close to Earth. False, as it never approached within 1.8 astronomical units. Others suggested the comet was emitting mysterious signals or exhibiting impossible behaviours. A few conspiracy theories emerged, positing that governments were concealing the true nature of 3I Atlas, or that the comet represented some form of extraterrestrial contact. Astronomers and science communicators work to counter these claims, though combating misinformation once it spreads widely remains challenging in the social media ecosystem. Public observatories and planetariums worldwide responded to the surge in interest by organising special viewing events and educational programs. On nights when 3I Atlas was well positioned, these facilities opened their telescopes to the public, allowing ordinary citizens to view the interstellar visitor with their own eyes. The experience of looking through a telescope at a comet from another star system proved powerful for many. There is something uniquely affecting about direct observation, seeing with one's own eyes rather than through processed images, that creates emotional connection to astronomical phenomena. Educational institutions also seized the opportunity. Schools incorporated 3I Atlas into science curricula, using it as a hook to teach about orbital mechanics, spectroscopy, interstellar space, and the scientific method. Universities organised public lectures where astronomers explained their research on the comet to packed auditoriums. Online educational platforms created content explaining the science, some achieving millions of views. The comet became a teaching tool, a concrete example that could make abstract concepts tangible and exciting. The international nature of the observation campaign highlighted science as a global collaborative endeavour. Telescopes in Chile, Hawaii, Spain, Australia, and numerous other locations all contributed to the comprehensive picture of 3I Atlas. Scientists from dozens of countries co-authored papers and shared data. When Mars spacecraft captured images of the comet, those images reflected decades of international cooperation in space exploration. In a world often divided by national interests and geopolitical tensions, the study of 3I Atlas demonstrated that science transcends boundaries, uniting humanity in common pursuit of knowledge. Several cultural commentators noted the timing of 3I Atlas's appearance, arriving during a period when global attention seemed increasingly fragmented, when social cohesion appeared fraying, when existential challenges from climate change to technological disruption generated anxiety about the future. Into this context came an object from literally another world, offering a reminder of cosmic perspective. Whatever human concerns seemed pressing, they occurred against a backdrop of a universe billions of years old, stretching across unimaginable distances, containing wonders we were only beginning to glimpse. For some, this perspective proved humbling. For others, inspiring. For many, both. The comet also sparked renewed discussion about humanity's place in the cosmos and the search for life beyond Earth. If comets from other star systems routinely pass through the galaxy, carrying material from distant planetary systems, what did this imply about the interconnectedness of stellar environments? Could organic material, or even microscopic life, survive the journey through interstellar space frozen in cometary ice? Might comets serve as vectors for panspermia, the theoretical transfer of life between worlds? While 3I Atlas offered no direct evidence relevant to these questions, its presence in our solar system reminded people that such questions were not merely philosophical speculation, but potentially answerable through scientific investigation. Artists found inspiration in the comet's story. Photographers created stunning composites and time-lapses showing the comet's motion against starry backgrounds. Digital artists produced imaginative renderings of what the comet might look like up close, or visualizations of its journey through interstellar space. Writers crafted poetry and prose exploring themes of cosmic wandering, ancient journeys, and the meeting of worlds. Musicians composed pieces inspired by the comet's visit, attempting to capture in sound something of the wonder and mystery it evoked. These creative responses demonstrated how scientific phenomena can transcend their technical details to become sources of aesthetic and emotional engagement. As November advanced and 3I Atlas faded from prominence both in the sky and in public consciousness, the intensity of global attention naturally waned. News cycles moved on to other stories, social media discussion shifted to newer topics. The comet's moment in the spotlight was passing, as transient as the comet's own passage through the inner solar system. But the impact of those months would persist. Thousands of people had been introduced to astronomy through 3i Atlas, some of whom would maintain that interest, perhaps even pursuing careers in science. The successful observation campaign had advanced scientific understanding and demonstrated the capability of modern astronomy to study interstellar objects in unprecedented detail. And in the collective cultural memory, there would remain the knowledge that for a brief period in 2025, humanity had watched a visitor from another star system pass through our cosmic neighbourhood, close enough to study, near enough to photograph, a tangible connection to the vast and ancient galaxy beyond our solar system's boundaries. October the 29th, 2025, 1437 Universal Time. In the cold vacuum of space, 210 million kilometres from Earth, 3i Atlas reached the perihelion point of its trajectory, the closest it would ever come to our Sun. At this moment, the comet experienced solar irradiation, at intensity it had not felt for billions of years, not since it orbited its own distant star in some long-ago epoch before being ejected into the interstellar void. The Sun's radiation, unfiltered by atmosphere, bathed the nucleus in searing heat, driving sublimation of ices at maximum rates, stripping away layers of ancient material, transforming the comet's appearance even as its trajectory carried it through this crucial point and out toward the outer solar system once again. From Earth, the moment passed unmarked by direct observation. The comet lay too close to the Sun in the sky, impossible to see against the overwhelming glare of our star. No telescope pointed toward perihelion at the instant it occurred. No human eye witnessed the actual moment when 3i Atlas rounded the Sun and began its outward journey. Yet the significance of the event transcended whether anyone watched. The perihelion passage represented a fundamental transition, the pivotal moment in the comet's biography, the point that divided approach from departure, brightening from fading, discovery from disappearance. The physics occurring at perihelion were both violent and subtle. The comet's nucleus, perhaps 3 kilometres across, rotated slowly through sunlight and shadow. The illuminated hemisphere facing the Sun received thermal energy at a rate of roughly 900 watts per square metre, about 2/3 what falls on Earth's surface at noon. But unlike Earth with its thick atmosphere to distribute and moderate heat, the cometary surface responded directly and immediately to this radiation. Surface temperatures climbed rapidly, reaching perhaps 200 to 250 Kelvin, well above the sublimation temperature of water ice, and far above that of the carbon dioxide ice that dominated 3i Atlas's composition. The sublimation itself occurred through a process both simple in principle and complex in detail. The ice molecules vibrating in their frozen lattice absorbed thermal energy until their vibrations became vigorous enough to break the weak bonds holding them in the solid state. They escaped directly to vapour, sublimation, without passing through a liquid phase, since cometary pressures are far too low to allow liquid to exist. The vapour expanded outward at speeds of hundreds of metres per second, carrying with it dust particles that had been embedded in the ice. This expanding plume of gas and dust formed the coma, glowing in sunlight and fluorescing as ultraviolet radiation drove chemical reactions. But not all the absorbed solar energy drove sublimation. Some heated the underlying layers, conducting downward into the nucleus interior. This created a temperature gradient, the surface warmer than the depths, and this gradient drove complex evolution in the nucleus structure. Subsurface ices, warmed but not yet hot enough to sublime directly to the vacuum, could migrate through pores and cracks, redepositing in cooler regions. Volatile species like carbon dioxide with lower sublimation temperatures could escape from beneath less volatile water ice, creating pressure that might fracture the overlying layers or force gas to vent through weaknesses in the structure. The mechanical stresses were considerable. As the nucleus rotated, regions cycled between heating and cooling, expanding when illuminated and contracting when in shadow. These thermal cycles, repeated many times during each rotation period, fatigued the already weak material. The nucleus, likely a loosely consolidated rubble pile rather than a solid monolith, might crack and shift under these stresses. The pressure of sublimating gas beneath a surface crust could lift and fracture that crust, creating new pathways for gas escape or exposing fresh, volatile-rich material. The perihelion environment tested the nucleus structurally in ways it had not experienced during its long interstellar drift, and whether it would survive intact remained uncertain until afterward. The gravitational environment added another layer of complexity. While the comet's own gravity was negligible, a person standing on the nucleus could easily jump to escape velocity. It was not zero. The escaping gas exerted pressure on the nucleus, a reaction force that slightly accelerated the comet in the direction opposite the most vigorous outgassing. These non-gravitational forces were small compared to the Sun's gravitational pull, but over time they could noticeably alter the comet's trajectory. Measuring these accelerations provided information about the distribution and magnitude of outgassing, helping constrain models of the nuclear structure and composition. As the comet passed through perihelion and began its outward journey, the thermal environment began to change. Solar flux decreased as distance increased, following the inverse square law. Twice the distance meant 1/4 the energy. But the nucleus did not cool immediately. Thermal energy absorbed near perihelion had conducted into the subsurface layers, creating a reservoir of heat that would continue driving sublimation for days or weeks afterward. This delayed response meant that peak activity often occurred not at perihelion itself but some days afterward, a phenomenon commonly observed in solar system comets and apparently shared by 3I Atlas. The moment also carried profound historical significance. 3C Atlas became only the third confirmed interstellar object observed passing through the inner solar system, and the second clearly identified as a comet. Its perihelion passage represented the most comprehensively documented encounter with an interstellar visitor to date, surpassing even the detailed observations of 2I Borisov. The data collected before, during, and after perihelion would be analysed for years, yielding insights into cometary physics, interstellar chemistry, and the diversity of planetary systems. For the scientific teams who had devoted months to studying 3I Atlas, perihelion marked both culmination and commencement. The intensive pre-perihelion observation campaign had achieved its goals, capturing detailed data about the comet's approach and peak activity. But now began the equally important post-perihelion phase, when observations would reveal how the close solar passage had affected the nucleus, whether fragmentation had occurred, how the outgassing patterns changed as the comet receded. The story was far from over. In some ways, it was only beginning its next chapter. In the centuries and millennia to come, 3I Atlas would slowly recede from the solar system, climbing back up the Sun's gravitational well until it reached and exceeded its original incoming speed. It would pass the orbit of Jupiter in March 2026, a final planetary encounter before departing the realm of the planets forever. Beyond Jupiter, it would continue outward through the outer solar system, a journey lasting years, gradually fading from visibility as distance and dimness combined to render it invisible even to the most powerful telescopes. Eventually it would cross the heliopause, the boundary where the solar wind gives way to the interstellar medium, returning to the darkness between stars from which it had emerged, and there it would continue, for eons beyond human comprehension, wandering through the galaxy on trajectories determined by gravitational encounters with other stars it would pass in the deep future. Perhaps billions of years hence it might enter another planetary system, warming once again under the light of a different sun, outgassing and glowing in another sky. Or perhaps it would drift forever between stars ancient and alone, carrying frozen within it the chemical signatures of the distant stellar nursery where it formed so long ago. But for this moment, this singular point on October 29th, 2025, it was ours to observe and wonder at. A visitor from the cosmic ocean beyond our shores, bringing news of other worlds and other times, had rounded our sun and would soon depart. The perihelion passage marked the apex of its visit and the beginning of farewell. In the endless expanse of space and time, this encounter occupied the briefest instant. Yet for those who witnessed it and studied it, the moment carried significance that would echo through their understanding of the universe for years to come. The cosmic visitor had reached its closest approach, and now, inevitable as gravity itself, it was beginning its journey home to the stars. The age of 3I Atlas represents a concept almost impossible for the human mind to fully grasp. When astronomers traced the comet's trajectory backward through space and analysed the chemistry frozen within its ices, they arrived at estimates suggesting this object might be more than 7 billion years old. 7 billion years. To put this in perspective, Our Earth formed 4.5 billion years ago. The Sun ignited from a collapsing cloud of gas and dust 4.6 billion years in the past. 3i Atlas, by these estimates, predates our entire solar system by billions of years. It is quite literally a relic from an earlier epoch of our galaxy's history, a frozen archive carrying information about cosmic conditions that existed before our world was born. The implications of this antiquity ripple outward in multiple directions, each raising profound questions about the nature and history of our galaxy. If 3i Atlas formed 7 billion years ago, it was born when the Milky Way was a younger, more violent place. Star formation rates were higher then. Massive stars lived and died in rapid succession, seeding the interstellar medium with heavy elements forged in their nuclear furnaces and dispersed in supernova explosions. The chemical composition of the galaxy has evolved over time, with each generation of stars slightly enriching the cosmic mix of elements heavier than hydrogen and helium. A comet from that earlier epoch would have formed from material with different elemental abundances than objects forming today. The specific chemistry observed in 3i Atlas offers tantalizing hints about these ancient conditions. Its extreme carbon dioxide to water ratio, the unusual metal emissions, the organic compounds detected in its coma. These features may reflect the composition of protoplanetary disks, as they existed billions of years before our solar system formed. If astronomers can decode these chemical signatures, they gain insight into how planetary systems formed under the different conditions of the early galaxy, when stellar metallicities were lower, when the interstellar environment contained less of the heavy elements crucial for rocky planet formation. But the comet's age also raises questions about its preservation. 7 billion years is an almost incomprehensible span of time. Stars are born, evolve through their life cycles, and die on timescales of millions to billions of years depending on their mass. Galaxies collide and merge. The universe itself is only about 13.8 billion years old, meaning 3 Atlas has existed for more than half of cosmic history. How does a small, fragile object of ice and rock survive unchanged through such epochs? The answer lies in the nature of interstellar space. Between the stars, conditions are as close to perfect preservation as exist anywhere in the universe. Temperatures hover just a few degrees above absolute zero. Densities are vanishingly low, with perhaps 1 atom per cubic centimetre, hard vacuum by any terrestrial standard. An object drifting through this environment experiences almost no erosion, no weathering, no chemical alteration beyond the slow cumulative effects of cosmic ray bombardment. It is the ultimate deep freeze, a cosmic cryogenic chamber where ancient material can survive essentially unchanged for eons. Yet even in the emptiness of interstellar space, change occurs. Cosmic rays, high-energy particles accelerated to near light speed by supernova remnants and other violent events, constantly bombard interstellar objects. These particles penetrate surface layers, breaking chemical bonds, creating new compounds, altering isotopic ratios through nuclear reactions. Over billions of years, this radiation processing modifies the surface chemistry, potentially to depths of meters or more. The surface of 3i Atlas observed in 2025 likely differs chemically from its pristine formation state, though the deep interior presumably remains largely unaltered, still preserving the original chemistry of its birth cloud. The comet's journey through space over those billions of years follows paths determined by gravity. After its ejection from its home planetary system, presumably during the chaotic planet formation epoch when gravitational interactions between growing planets and smaller bodies were common, 3 Atlas would have drifted outward from its parent star, eventually reaching interstellar space. From there, its trajectory would have been shaped by gravitational interactions with other stars it passed, each encounter slightly altering its velocity and direction. These accumulated perturbations, compounded over billions of years, determine the path that eventually brought it to our solar system. Tracing this path backward with certainty is impossible. The positions and velocities of stars change significantly over millions of years, and uncertainties compound rapidly when trying to reconstruct trajectories over billions. Nevertheless, statistical analysis can identify the region of the galaxy where 3 Atlas likely originated. The current best estimates suggest it came from the galactic thick disk, a population of older stars surrounding the galaxy's main disk. This thick disk contains stars that formed when the Milky Way was young, consistent with the comet's estimated age. Stars in this region have different chemical compositions and orbital characteristics than younger stars in the thin disk where our Sun resides. If 3I Atlas did originate in the thick disk, its journey to our solar system would have been extraordinarily lengthy. The thick disk extends several thousand light-years above and below the galactic plane. Typical velocities of objects within it are tens of kilometers per second. Travelling at such speeds, 3I Atlas might have required hundreds of millions of years or more to cover the distance from its formation location to our solar system, even travelling in a relatively direct path, which it almost certainly did not. The comet's path through space would have been anything but straight, deflected repeatedly by gravitational encounters with stars, wandering through the galaxy on a chaotic trajectory, ultimately bringing it to this moment of illumination under our Sun. The realization that 3 Atlas might be older than our solar system transforms how we think about it. This is not merely a comet from another star system, interesting as that alone would be. This is a messenger from the deep past, from an era when the galaxy was younger, when the conditions that would eventually lead to our Sun and Earth and ourselves were only beginning to take shape. The molecules frozen within it, now sublimating and fluorescing in our telescopes, were assembled before our world existed. They carry information about cosmic chemistry as it existed in that ancient epoch, a direct sample of conditions billions of years in the past. Moreover, if interstellar space contains a population of such ancient objects, comets and asteroids ejected from planetary systems throughout galactic history, then these wanderers represent a distributed archive of galactic evolution. Each object potentially preserves the chemistry of its formation era and location. By studying multiple interstellar visitors from different epochs and regions, astronomers could in principle reconstruct the chemical history of the galaxy, tracking how element abundances and isotopic ratios have changed over billions of years. 3 Atlas offers a single data point in this vast archive, but it is a data point from deep time, a sample of ancient matter that has found its way to our instruments. The philosophical dimension of encountering an object older than our solar system should not be overlooked. We humans, as a species, are perhaps 300,000 years old, a mere instant on cosmic timescales. Our civilization, our science, our ability to build telescopes and analyze spectra has existed for mere centuries, yet we find ourselves able to study an object that has wandered the galaxy for billions of years, that existed before our planet formed, that will continue long after our Sun has exhausted its fuel and our Earth has been consumed. There is something simultaneously humbling and elevating in this realization, humbling in revealing our cosmic insignificance, elevating in demonstrating that despite that insignificance, we can understand and investigate phenomena vastly older and larger than ourselves. As 3 Atlas fades from view in the months following its perihelion passage, returning to the darkness from which it emerged, it carries with it these layers of significance. It is simultaneously an astronomical object to be studied with instruments and mathematics, a chemical sample to be analysed with spectroscopy and laboratory simulations, and a symbol of cosmic time, of the ancient processes that have shaped our galaxy over eons. Understanding what it is requires science, appreciating what it means requires imagination, the ability to envision spans of time and space beyond everyday experience. To grasp that we live in a universe far older and larger than intuition suggests, full of wanderers like 3I Atlas that connect us across the gulfs of space and time to other worlds, other eras, other possibilities for how matter can organize itself into the complex structures we observe throughout the cosmos. The search for life beyond Earth represents one of humanity's most profound scientific endeavors, touching on fundamental questions about our place in the universe and the nature of biological organization itself. Are we alone? A singular occurrence of self-replicating chemistry that somehow achieved consciousness in a cosmos otherwise barren of life? Or is life common, emerging wherever conditions permit, meaning the universe teems with biology even if we have not yet detected it? Interstellar objects like 3I Atlas, while not directly answering these questions, provide crucial pieces of evidence that inform how we think about life's cosmic prevalence. The connection between interstellar comets and the origin of life begins with chemistry. Life as we know it requires certain basic ingredients: liquid water, organic carbon compounds, energy sources to drive chemical reactions, and time for complex molecules to form and evolve. Comets contain many of these ingredients. Their ices include water, obviously, but also carbon dioxide, methane, ammonia, and more complex organic molecules. When comets formed in the outer reaches of protoplanetary disks, they incorporated the rich organic chemistry that existed in those cold regions, where molecules could stick together without being destroyed by the heat closer to young stars. Laboratory analysis of samples from solar system comets, particularly material returned by spacecraft missions like Stardust and Rosetta, have revealed remarkable chemical complexity. Comets contain amino acids, the building blocks of proteins. They harbour polycyclic aromatic hydrocarbons, complex ringed molecules rich in carbon. They carry simple sugars and various other organic compounds. This chemistry arose through processes occurring in the protoplanetary disk and perhaps even earlier, in the interstellar cloud from which the disk formed. Cometary material represents, in a sense, prebiotic chemistry, the complex organic molecules that might have served as raw material for life's emergence. When the young Earth was being bombarded by comets and asteroids during the late heavy bombardment period some 3.9 billion years ago, these impacts delivered not just water filling the oceans, but also a rich inventory of organic molecules. Whether these molecules played a crucial role in life's origin on Earth remains debated, but they certainly contributed to the chemical environment in which life emerged. In this view, comets served as delivery vehicles for life's ingredients, bringing together in one location the water and organics necessary for biology to begin. Thrusty Atlas extends this perspective beyond our solar system. If comets from other stellar systems also contain organic compounds, and there is no reason to believe they do not, then the chemical ingredients for life might be distributed widely throughout the galaxy. Every star system that forms produces comets. Many of these comets are ejected into interstellar space during the planet formation process. These ejected comets carry with them the organic chemistry of their home systems. If some of these interstellar wanderers subsequently enter other planetary systems, they deliver alien organics, chemistry produced around a different star to new worlds. This process, the transfer of material between stellar systems via interstellar objects, has profound implications. It suggests that planetary systems are not entirely isolated, that chemistry produced around one star can eventually reach planets around other stars. If life's origin requires specific organic molecules or particular chemical configurations, and if these arise in some stellar environments but not others, then interstellar comets could serve as vectors, distributing life's ingredients throughout the galaxy. Planetary systems that might otherwise lack crucial prebiotic compounds could receive them via interstellar delivery. The hypothesis extends further into more speculative territory. Could life itself travel between stars aboard comets? This idea, called panspermia, proposes that microorganisms frozen in cometary ice might survive the journey through interstellar space and seed life on worlds they subsequently encounter. The challenges are immense. Interstellar space is cold, but it is also bathed in radiation that would damage biological molecules. The journey times are enormous, millions or billions of years, far exceeding any timescale on which we know life can remain viable even in dormancy. The probability that an interstellar comet would encounter a suitable planet and deliver its frozen cargo intact seems vanishingly small, yet entirely dismissing panspermia would be premature. Laboratory experiments have shown that certain microorganisms, particularly bacterial spores, can survive remarkably harsh conditions, vacuum, radiation, extreme temperatures, for extended periods. Frozen deep within a cometary nucleus, shielded from radiation by overlying meters of ice and rock, might some organisms survive even interstellar timescales? We do not know, because we have no way to test survival over millions of years. But the possibility, however remote, cannot be categorically excluded with current knowledge. Studying the chemistry of 3I Atlas and future interstellar comets provides data relevant to these questions. By analysing what organic compounds exist in comets from other stellar systems, astronomers can assess whether cometary chemistry is universal or varies between different stellar environments. If all comets show similar organic inventories, regardless of origin, this suggests that the chemical processes producing these compounds are robust and universal. If significant variation exists, this might indicate that different stellar environments produce different chemistry, with implications for where life might arise. The search for biosignatures, direct evidence of life, in cometary material remains a distant goal, but not an impossible one. Future missions might rendezvous with an interstellar object while it passes through our solar system, collecting samples of its coma or even landing on its nucleus to gather material for analysis. Such samples could be searched for signs of biological activity, molecular structures too complex or specific to arise through normal chemistry, isotopic ratios characteristic of biological processing, or even preserved cellular structures if we are extraordinarily fortunate. The probability of finding such evidence is low, but the scientific payoff would be revolutionary. Beyond the direct question of whether comets carry life, studying interstellar objects informs the search for life through the information they provide about planetary system diversity. Every interstellar visitor carries chemical signatures of the conditions in its home system. By studying these signatures, we learn about the range of environments in which planets form, the variety of chemical compositions possible, the different evolutionary paths that stellar systems follow. This diversity matters for astrobiology because life's emergence depends on environment. Understanding the full range of possible planetary environments helps identify where to search for life and what signs might indicate its presence. The detection of organic molecules in 3I Atlas's coma, while not surprising given what we know about comets, still carries significance. It confirms that the chemical processes producing organic compounds in our solar system also operate around other stars. It demonstrates that the building blocks of life, or at least the complex carbon chemistry that might lead to life, exist throughout the galaxy, not just in our local neighborhood. Each interstellar visitor that shows similar chemistry strengthens the case that the universe is chemically suited for life, even if we have not yet found life itself beyond Earth. SETI, the search for extraterrestrial intelligence, also finds motivation in objects like 3I Atlas, though the connection is less direct. If interstellar objects are common, and if civilizations arise around some stars, might such civilizations deliberately use interstellar objects as vehicles or beacons? Could a sufficiently advanced civilization attach instruments or messages to comets and asteroids, using them to explore or communicate across interstellar distances? These ideas remain speculative, but they illustrate how interstellar visitors inspire thinking about cosmic possibilities beyond conventional astronomical phenomena. The visits of Oumuamua, 2I Borisov and 3I Atlas, occurring within just 8 years, suggest that interstellar objects pass through our solar system regularly, perhaps several per year if our detection capabilities were perfect. Each represents an opportunity to sample material from another stellar system, to study chemistry from different cosmic environments, to search for the unexpected. As detection technology improves and more interstellar visitors are discovered, the study of these objects will become a routine part of astronomy. Eventually, we may develop the capability to intercept them with spacecraft, collecting samples for detailed analysis in terrestrial laboratories. Such sample return missions would revolutionize our understanding of interstellar chemistry and, by extension, the cosmic context for life. Having actual material from another star system available for analysis with the full suite of laboratory instruments, not just remote spectroscopy, but direct chemical analysis, isotopic measurements, molecular characterization, would provide information impossible to obtain through telescopic observation alone. Among the questions such samples might answer: what organic molecules exist in pristine interstellar material? Do amino acids from other stellar systems show the same handedness preference as those on Earth? Are there chemical signatures of biological activity, or can we definitively rule out life's presence? 3I Atlas, while now fading from view, has contributed to this broader program of using interstellar objects to understand life's cosmic context. Its chemistry adds another data point to the growing catalogue of interstellar compositions. Its visit has energized efforts to detect and study future visitors. And it has reminded us that our solar system is not isolated, that we inhabit a galaxy full of wandering objects carrying chemistry and history from other worlds. In the search for life beyond Earth, every piece of information matters. Every window into the diversity of cosmic environments helps constrain where and how biology might arise. Interstellar visitors like 3I Atlas open such windows, offering glimpses of conditions around other stars, and in doing so they inform our understanding of whether we are alone or part of a living cosmos. The intensive study of 3I Atlas during its passage through the inner solar system was possible only because of remarkable technological capabilities that previous generations of astronomers could scarcely have imagined. The telescopes, instruments, spacecraft, and analytical techniques brought to bear on this single comet represent the culmination of decades of development in observational astronomy, space exploration, and data science. Understanding what made this level of detailed study possible illuminates both how far astronomical technology has advanced and what future capabilities might enable as we encounter more interstellar visitors. Consider first the telescopes themselves. The Hubble Space Telescope, launched in 1990, represents the pinnacle of optical astronomy from orbit. Its 2.4-meter mirror, freed from the distortions of Earth's atmosphere, achieves resolution impossible from ground-based facilities without adaptive optics. The images Hubble captured of 3I Atlas revealed fine structure in the comet's coma and tails, details that would have been blurred beyond recognition by atmospheric turbulence had observations been attempted from Earth's surface. Yet Hubble operates in visible and ultraviolet light, capturing only part of the electromagnetic spectrum. The James Webb Space Telescope, which began science operations in 2022, complements Hubble by observing in infrared wavelengths. Webb's 6.5-meter segmented mirror, vastly larger than Hubble's, combined with its infrared sensitivity, allows it to detect thermal emission from objects too cool or distant to shine brightly in visible light. For 3I Atlas, Webb's observations revealed the comet's temperature distribution and measured infrared emission from molecules like carbon dioxide that are difficult to study at other wavelengths. Webb's spectroscopic capabilities provided detailed chemical analysis, measuring not just what elements were present but their isotopic ratios and molecular configurations. Ground-based telescopes have not been left behind by space observatories. Modern ground-based facilities use adaptive optics, systems that measure atmospheric distortions in real time and compensate using deformable mirrors that change shape hundreds of times per second. This technology allows ground-based telescopes to achieve resolution approaching that of space-based instruments, at least for bright objects. The Very Large Telescope in Chile, with its 4 8.2-meter mirrors and sophisticated adaptive optics, captured spectroscopic data of 3I Atlas with extraordinary resolution, revealing emission lines from dozens of molecular species. The Gemini Observatory's twin telescopes in Hawaii and Chile provided both hemispheric coverage and exceptional image quality. Their observations documented the comet throughout its apparition, from early detection through perihelion to post-perihelion fade. The ability to observe from both northern and southern hemispheres ensured continuous coverage as the comet's position in the sky changed, eliminating gaps that might otherwise have occurred when the comet was poorly placed for observation from a single location. But telescopes and their optical systems are only part of the story. The instruments attached to these telescopes, the cameras, spectrographs, and photometers that actually detect and analyze light, have undergone revolutionary development. Modern astronomical cameras use charge-coupled devices or newer CMOS sensors with exquisite sensitivity, capable of detecting individual photons. The quantum efficiency of these detectors, the fraction of incoming photons actually detected, exceeds 90% for some wavelengths, compared to perhaps 1–2% for photographic plates used in earlier eras. This means modern instruments can detect objects hundreds of times fainter than was possible just decades ago. Spectrographs have similarly advanced. Modern instruments achieve spectral resolution, the ability to distinguish closely spaced wavelengths, that allows measurement of Doppler shifts corresponding to velocities of meters per second. This resolution enables astronomers to study not just what molecules are present in a comet's coma, but how fast they are moving, revealing the dynamics of gas expansion and the distribution of velocities among different species. Integral field spectrographs can capture spectra of every point in a two-dimensional field simultaneously, creating three-dimensional data cubes where 2 dimensions are spatial and the third is wavelength. For an extended object like a comet, this allows mapping of how composition varies across the coma. The spacecraft observing 3I Atlas contributed unique perspectives impossible to achieve from Earth. Mars orbiters viewed the comet from a different angle, providing parallax that helped constrain three-dimensional structures. The JUICE spacecraft, traveling through the outer solar system, observed 3i Atlas without the scattered sunlight that creates background glow in observations from Earth's vicinity. These different vantage points provided complementary data that, combined, created a more complete picture than any single observatory could achieve. Behind all these observational capabilities lies an often underappreciated technology: data processing and analysis. Modern astronomical instruments generate prodigious quantities of data. A single night's observation with a large telescope might produce gigabytes or terabytes of information. Processing these data, calibrating images, removing instrumental artifacts, extracting spectra, measuring positions and brightnesses requires sophisticated software running on powerful computers. Machine learning algorithms increasingly assist in tasks like identifying faint signals in noisy data or classifying spectral features. The coordination of this global observing campaign itself required technological infrastructure. Astronomers communicated via email and video conferencing, sharing data through internet-connected servers, coordinating schedules to ensure optimal coverage. The Minor Planet Center collected observations from hundreds of contributing observatories, maintained databases of orbital elements, and disseminated predictions of where the comet would be visible. This coordination network, largely invisible to the public, enabled the distributed global effort to function as a coherent whole. Looking forward, new technologies promise even more powerful capabilities for studying future interstellar visitors. The Vera Rubin Observatory, scheduled to begin operations in the late 2020s, will survey the entire visible sky every few nights, with an 8.4-meter telescope and a 3.2 gigapixel camera. This survey is expected to discover numerous interstellar objects per year, catching them earlier when they are still distant and allowing longer observation baselines. Early detection is crucial for mission planning if we want to send spacecraft to intercept these visitors. The extremely large telescope, under construction in Chile with a 39-meter primary mirror, will be the largest optical telescope ever built when it comes online in the early 2030s. Its light-gathering power and resolution will enable detailed spectroscopy of faint objects, potentially revealing chemical signatures in interstellar visitors that current instruments cannot detect. Similarly, the 30-meter telescope and Giant Magellan Telescope, other extremely large telescopes in development, will provide unprecedented capabilities for studying transient phenomena. Future space missions specifically designed to rendezvous with interstellar objects are being conceptualized. These would use high-speed propulsion systems, perhaps solar sails or nuclear propulsion, to match velocities with fast-moving interstellar visitors. Such missions could study these objects up close, landing instruments on their surfaces or collecting samples of their comae for return to Earth. The technological challenges are formidable. Interstellar objects move fast relative to the solar system, and catching up with them requires velocities beyond current spacecraft capabilities. But conceptual designs exist, and the scientific payoff would be enormous. The study of 3i Atlas demonstrates what becomes possible when advanced technology is brought to bear on astronomical phenomena. Every spectrum, every image, every measurement relied on sophisticated instruments, powerful telescopes, and complex data processing. Yet even with these capabilities, mysteries remained, observations left questions unanswered, and the comet's nature was not fully decoded. This reminds us that technology, however advanced, provides tools for investigation but not automatic understanding. The data must still be interpreted, models tested against observations, alternative hypotheses evaluated. Technology enables scientific study, but science itself remains a human endeavor, requiring creativity, insight, and critical thinking to transform data into understanding. As 3i Atlas recedes into the distance, the technological systems that studied it turn toward other targets. The telescopes point toward other celestial objects. The spacecraft continue their missions. The data analysis pipelines process information from new observations. But the experience gained, the techniques refined, and the coordination networks established during the 3i Atlas campaign will serve astronomy well when the next interstellar visitor arrives. We are better prepared now, more capable, more coordinated. Each such visitor teaches us not only about the object itself, but about how to study such objects. The technology that made 3i Atlas science possible will continue to advance, ensuring that future interstellar visitors receive even more comprehensive scrutiny, yielding ever deeper understanding of the cosmos beyond our solar system's boundaries. Beyond the scientific data and technological achievements, the visit of 3i Atlas invites contemplation of deeper questions that transcend the merely empirical. What does it mean that objects from other star systems pass through our cosmic neighbourhood? How should we understand our place in a universe where ancient ice from alien worlds can arrive unannounced and depart just as suddenly? These questions occupy the borderland between science and philosophy, where factual observation meets interpretive meaning-making, where we confront not just what is, but what it signifies. Consider the perspective that 3i Atlas offers on cosmic time. We humans live our lives on timescales of decades, perhaps a century if we are fortunate. Civilizations rise and fall over millennia. Species evolve over millions of years. Even Earth's geological history, vast as it seems, spans some 4.5 billion years. Yet 3i Atlas may have been wandering the galaxy for 7 billion years, longer than our planet has existed, longer than our sun has burned. It existed before our world formed, drifting through the darkness when the matter that would become our solar system was still dispersed in interstellar clouds. It will exist long after our sun has exhausted its fuel and our Earth has become uninhabitable. This temporal vastness challenges our intuitive sense of duration and permanence. We live in a universe where the typical is ancient beyond our comprehension, where our entire history occupies an imperceptible instant in cosmic spans. The Hubble Space Telescope, one of humanity's greatest achievements, has been in orbit for 35 years as of 2024, less than 1/billionth the age of 3i Atlas. Everything humans have ever accomplished, all of recorded history, all the rise and fall of empires and the advancement of knowledge, has occurred in a time span that is cosmically negligible compared to the age of this wandering ice ball. Yet here we stand, ephemeral beings on a young world, capable of studying this ancient visitor, understanding where it came from and what it is made of, predicting where it will go. There is something profound in this capacity. We exist for mere instants on cosmic timescales, yet we can comprehend and investigate phenomena that dwarf our existence. Our understanding transcends our lifespan. The knowledge we gain, encoded in books and databases and shared through culture, persists beyond individual lifetimes, building across generations into a collective understanding that achieves something approaching cosmic perspective. The spatial dimension of 3i Atlas's journey invites similar reflection. The distances between stars are so vast that even light, the fastest thing in the universe, requires years to cross them. 3i Atlas has travelled across multiple light years, a journey that for it required millions or billions of years of drift through interstellar space. The nearest star to our Sun lies 424 light-years distant, a gulf so immense that our fastest spacecraft would require tens of thousands of years to cross it. Yet despite these immensities, objects do traverse interstellar space. Connections exist between stellar systems, however tenuous and slow. This challenges notions of cosmic isolation. We might think of star systems as islands, separated by oceans of darkness, each isolated in its own gravitational domain. But interstellar objects demonstrate that matter flows between systems. Chemistry produced around one star eventually reaches others. What happens in distant stellar environments eventually propagates, carried by wandering comets and asteroids that serve as vectors of exchange across interstellar gulfs. The galaxy, vast as it is, possesses connectivity, threads of matter and energy linking its components across space and time. The question of meaning arises naturally when contemplating such cosmic interconnection. Does the arrival of 3i Atlas in our solar system mean anything? Science would say no. It is simply the result of deterministic physical processes, gravity and momentum playing out over eons, with no purpose or significance beyond the facts of its occurrence. The comet has no awareness of where it travels or what it passes. Its journey is not a quest or mission, but merely the consequence of initial conditions and the laws of physics. To project meaning onto it would be anthropomorphism, imposing human categories onto indifferent natural phenomena. Yet humans are meaning-making creatures. We cannot help but interpret, find significance, construct narratives. The visit of an interstellar object becomes more than just an astronomical event. It becomes an encounter, a reminder of the universe's vastness and strangeness, an invitation to expand perspective beyond everyday concerns. The meaning may not inhere in the comet itself, but in what its presence evokes in us: wonder, curiosity, humility, the desire to understand. These responses, while subjective, are not arbitrary. They reflect something genuine about the human condition, our capacity to be moved by the sublime, to find in natural phenomena prompts for contemplation of our place in the cosmos. The comet also raises questions about rarity and cosmic diversity. How unusual is 3I Atlas? If we could observe the galaxy from an external perspective, surveying all the interstellar objects drifting through it, would 3I Atlas be typical or exceptional? We have detected only 3 confirmed interstellar visitors, far too few to characterize the population. Each has been distinctive: Oumuamua with its peculiar elongation and non-gravitational acceleration, 2I Borisov with its familiar cometary behavior, 3 Atlas with its unusual chemistry and sunward jet. Are these representative of broader categories, or are interstellar objects so diverse that categorization becomes meaningless? This question bears on fundamental issues of cosmic variability. Does the universe produce similar things in similar ways everywhere? Or does it generate endless variation, each stellar system and each epoch yielding unique outcomes? The answer matters for how we think about phenomena ranging from planet formation to the emergence of life. If processes are universal, producing similar results under similar conditions, then we can extrapolate from local knowledge to cosmic understanding. If variation dominates, if each system is sui generis, then general principles become harder to establish, and the cosmos is more complex and diverse than simple models suggest. Philosophy has long grappled with the relationship between human existence and cosmic vastness. The ancient Greeks wondered about the nature of the heavens and our place beneath them. Medieval theologians constructed cosmologies with Earth and humanity at the centre, reflecting religious understandings of cosmic purpose. The Copernican revolution displaced Earth from that central position, a shift with profound philosophical implications. We were not the centre around which everything revolved, but merely one world among others, orbiting an ordinary star in an unremarkable location. Each subsequent discovery, the vastness of the galaxy, the existence of countless other galaxies, the universe's incredible age, has reinforced this lesson in cosmic humility. Yet this humility need not lead to nihilism or insignificance. The fact that we are small and brief on cosmic scales does not negate the reality and importance of our existence. Consciousness, intelligence, the capacity for understanding, these remain remarkable regardless of cosmic context. A universe that contains beings capable of studying 3I Atlas and decoding its history is a universe where, at least in some corners, matter has organized itself into forms that can comprehend and investigate their surroundings. This seems significant, even if the universe as a whole remains indifferent to it. Some philosophers and scientists have proposed that the universe's apparent fine-tuning for life and complexity suggests deeper purpose or design. Others counter that multiple universes or selection effects adequately explain apparent fine-tuning without invoking teleology. 3 Atlas does not resolve these debates, but its existence and our ability to study it participate in them. We are part of a universe where interstellar exchange occurs, where ancient objects carry chemistry across light years, where matter formed around dying stars billions of years ago can reach worlds like ours. Whatever one's philosophical orientation, this seems remarkable. As 3I Atlas departs, returning to the interstellar darkness, it leaves us not with answers but with enriched questions. We understand more about cometary physics, about interstellar chemistry, about our capacity to detect and study cosmic wanderers. But we also confront more vividly the vastness of time and space, the smallness of our place within it, and yet simultaneously our remarkable capacity to comprehend and investigate these scales. The comet's visit was brief, but its implications, scientific, philosophical, existential, will resonate long after it has faded from view, receding toward future encounters with other stars, other worlds, perhaps other beings who might someday notice its passage and wonder, as we have, what this ancient wanderer signifies about the nature of the cosmos and their place within it. As 3 Atlas fades from view in early 2026, continuing its outward journey toward the heliopause, an eventual return to interstellar space, the time has come to assess the legacy of its visit. What has changed because this particular comet, from among the countless trillions wandering the galaxy, happened to pass through our solar system in 2025? The answers operate on multiple levels, from technical advances in astronomical observation to shifts in public consciousness about our place in the cosmos, from specific scientific discoveries to broader cultural impacts that will shape how humanity thinks about interstellar visitors in the decades to come. The most immediate legacy lies in the data itself. The observations collected during the 7 months of intensive study, from early discovery in July through post-perihelion observations in January 2026, constitute the most comprehensive dataset ever assembled for an interstellar object. Thousands of images, hundreds of spectra, photometric measurements tracking brightness variations on timescales from minutes to months, measurements from across the electromagnetic spectrum from radio to ultraviolet. All of this information now resides in astronomical archives, available for analysis and reanalysis for years to come. The initial scientific papers, published during and immediately after the apparition, represent only the beginning of what this dataset will reveal. Future researchers will return to these observations with new questions, new analytical techniques, new theoretical frameworks, extracting insights that current analysis might miss. The specific scientific findings have already begun reshaping understanding of cometary physics and interstellar chemistry. The confirmation that interstellar comets can have compositions significantly different from solar system comets, 3 Atlas's extreme carbon dioxide dominance, indicates that planet formation conditions vary between stellar systems more than some models predicted. This will inform theories of protoplanetary disk evolution and the diversity of planetary architectures throughout the galaxy. The unusual metal emissions, particularly the high nickel to iron ratio, suggest chemical processes or formation environments not encountered in our solar system, expanding the known range of cometary compositions. The anti-tail phenomenon, controversial as it was during the comet's apparition, has contributed to understanding of cometary jet dynamics. Whether ultimately explained by large particle ejection, specific viewing geometries, or unusual outgassing patterns, the prominence of this feature in 3I Atlas has prompted more detailed modelling of how material escapes from cometary nuclei and how jets form and evolve. The transition from prominent sunward jet pre-perihelion to more conventional appearance post-perihelion has been documented in unprecedented detail, providing observational constraints that models must match. Future studies of solar system comets will pay closer attention to similar features, now recognized as potentially more common than previously thought. The observational campaign itself established protocols and coordination mechanisms that will prove valuable for future interstellar visitors. The rapid mobilization of global observing resources, the coordination between space-based and ground-based facilities, the sharing of data and analysis across research groups, these represent achievements in scientific collaboration that transcend the study of any single object. When the next interstellar object is discovered, astronomers will be better prepared, with established procedures for triggering coordinated observations, proven techniques for rapid characterization, and communication networks already in place. The learning curve has been climbed. Future responses will be faster and more efficient. Technologically, the campaign demonstrated capabilities and revealed limitations that will guide future development. The ability to detect, track, and characterize an interstellar object from initial discovery through complete passage was successfully demonstrated, but gaps and shortcomings became apparent. The inability to observe during the perihelion blackout, when the comet was closest to the Sun, highlighted the value of having observational assets positioned away from Earth-Sun line. The difficulty of measuring rotation periods and nucleus sizes for highly active comets indicated where better techniques or more sensitive instruments are needed. These lessons inform planning for next-generation telescopes and space missions. The push for rapid response spacecraft missions capable of intercepting interstellar objects has been energized by 3I Atlas's visit. Conceptual designs that seemed speculative before now have concrete targets they could have studied, making the case for development more compelling. Proposals for pre-positioned spacecraft that could be quickly dispatched to intercept interstellar visitors, or for spacecraft with sufficient propulsion to launch and catch up with newly discovered objects, have moved from theoretical to seriously considered. While no such mission yet exists, the political and scientific will to develop this capability has strengthened, increasing the likelihood that future interstellar visitors might be met by spacecraft rather than merely observed from afar. The public engagement aspect of 3I Atlas's visit may ultimately prove as significant as the scientific findings. Millions of people who might never otherwise encounter astronomy learned about interstellar objects, comets, spectroscopy, and orbital mechanics through coverage of 3I Atlas. Public observatories reported record attendance during the comet's brightest phase. Amateur astronomy equipment sales increased. Online astronomy content saw surges in viewership. While public attention is transient, 3I Atlas has already largely faded from general awareness. Some fraction of those touched by the comet's story will maintain interest, perhaps pursuing education in science or supporting public funding for astronomy. The cultural impact of inspiring wonder about the cosmos has ripple effects difficult to quantify but nonetheless real. Educational institutions now have a recent concrete example when teaching about comets, orbital mechanics, and interstellar space. Textbooks will be updated to include 3I Atlas, alongside Oumuamua and 2I Borisov in discussions of interstellar visitors. Students encountering this material will learn not from abstract discussions, but from real events that occurred within their lifetimes, making the science more immediate and relevant. The pedagogical value of recent discoveries cannot be overstated. They demonstrate that science is not a closed body of established knowledge, but an ongoing process of discovery where new phenomena continue to be revealed. The philosophical and cultural contemplation sparked by 3I Atlas's visit has enriched public discourse about cosmic perspective. Articles and essays exploring what it means to encounter an object older than our solar system, videos explaining the vastness of interstellar space, social media discussions about whether we are alone in the universe. All of these represent the comet's visit rippling through culture in ways beyond pure science. The comet became a prompt for reflection on time, space, origins, and destiny, themes that resonate across cultures and speak to fundamental human concerns about our place in the cosmos. The preparation for future interstellar visitors has already begun in earnest. Survey telescopes designed to detect asteroids and comets now include capabilities specifically aimed at early identification of interstellar objects. Algorithms for distinguishing hyperbolic orbits from elliptical ones have been refined. Alert systems ensure that potential interstellar objects are flagged immediately for follow-up observation. The astronomical community is actively watching for the next visitor, equipped with experience and infrastructure that make early detection and comprehensive characterization increasingly probable. The question of nomenclature has been addressed. The Minor Planet Center and International Astronomical Union have established clear designation schemes for interstellar objects, ensuring that future discoveries will be consistently named and catalogued. This may seem like a minor bureaucratic detail, but standardized nomenclature facilitates communication and cataloging, ensuring that information about these objects remains accessible and properly attributed as the number of discoveries grows. In the decades to come, as more interstellar objects are discovered and studied, 3I Atlas will occupy a particular place in this growing catalogue. It was the third confirmed, the second clearly identifiable as a comet, the first to display certain specific features prominently, the most comprehensively studied up to its time. These distinctions ensure it will be remembered and referenced, a touchstone in the developing understanding of the interstellar population. Future comparative studies will include 3I Atlas in their samples, using its well-characterized properties as benchmarks against which newer discoveries are evaluated. The comet's legacy also includes the questions it left unanswered. What exactly determined its unusual composition? Why was its sunward jet so prominent compared to other comets? What is its precise age and from which specific star system did it originate? These open questions will motivate future research, driving development of better observational capabilities and more sophisticated theoretical models. Science advances not just by answering questions, but by formulating new ones, and 3I Atlas has provided a rich supply of mysteries to investigate. Perhaps most significantly, 3I Atlas has normalized the concept of interstellar visitors. Before Oumuamua's discovery in 2017, interstellar objects were theoretical predictions, expected to exist but never observed. Now, with 3 confirmed discoveries in 8 years, their reality is established. They are no longer exotic curiosities but recognized components of the solar system's environment, transient visitors that come and go but whose presence is expected. This conceptual shift, from might exist to regularly observed, changes how astronomers think about the solar system's boundaries and humanity's relationship with the broader galaxy. As 3I Atlas continues its journey, now invisible to human observation, carrying its ancient ices back to the interstellar medium from which it came, it leaves behind a changed scientific landscape. We understand more because it came. We're better prepared for the next visitor because we studied this one. We have been reminded vividly and concretely that our solar system is not isolated but connected to the galaxy that surrounds it, that objects formed around other stars can reach our neighbourhood, that the universe is full of wanderers whose chance passages through our space can teach us about cosmic diversity and our place within it. The legacy of 3I Atlas is not just the data collected or the papers published, but the expanded perspective it has given us on what is possible, what exists beyond our immediate surroundings, and what we might discover next time the cosmos sends an ancient messenger our way.